I'll be chairing. Yep, thanks, Neil. I'll be chairing the sessions this morning and this afternoon. I guess all day today. The first speaker up is the co-chair of the science collaboration, Neil Brandt, to give a welcome and introduction. And I'll just say, for the benefit of the speakers, I'm going to keep really strictly to time, because we have a tight schedule and people in lots of different time zones. So I'll try to give you like a 3-minute warning before your time is done, but we'll want to make sure we move on at exactly the time that we need to, if not slightly earlier. All right, Neil, I'll turn it over to you.
Thanks. So I'm going to start with just a 5-minute introduction and welcome. So first of all, welcome everybody to Supermassive Black Hole Studies with a Legacy Survey of Space and Time for 2022. This is our third remote summer meeting like this. This year, unlike previous years where all talks were almost entirely science focused, this year we're going to have more of a combination of practical planning talks, given that Rubin operations are not so far away, as well as a lot of exciting science talks as well. I want, of course, to recognize the organizers who worked very hard with me to make the meeting possible. Gordon Richards, Demetra, Cicco, Matthew Temple, they all put in a good amount of effort to make this possible. Hopefully, we have the Zoom working okay. If you hear of someone having Zoom troubles, please let the organizers know by email. We don't have professional Zoom support or anything like that, but we'll do our best to try to be helpful. And the emails are in the logistics email that you were all sent. We want to run this meeting as a Zoom meeting, which is distinct from a Zoom webinar. That will allow the best interactions possible, where people can ask questions directly after each talk. But for that to work, given that we have more than 100 registrants, we would request that all attendees just be very careful to mute their microphones when not speaking, so we're not hearing things going on in your house or whatever, your office. And then we just also request, given that 100 people are involved, that everybody just try to be extra reasonable and polite, so we can all have a positive and productive meeting. Strictly, the meeting will follow the Aegean science collaboration and standard AAS policies regarding professional conduct and anti-harassment. So please be aware of those and please follow those, and they're linked in the organizational email. Other points quickly, the meeting is going to be video and audio recorded. In fact, the recording's already started using Zoom, and that's so that we can release the meeting on YouTube. And that serves as, valuable outreach to people who may have interest in joining the Aegean Science Collaboration and wants to know what we're up to. And so clearly attending the meeting implies willingness to be recorded in that way, and I just want to make sure everyone's aware of that. Also note that at the end of each day, after all of the organized talks, we've budgeted about 45 minutes for, semi-structured, I'd say, semi-structured discussions. Today, for example, Franz Bauer is going to lead a discussion of the Survey Cadence Optimization Committee, which is clearly critically important. On Wednesday, Sebastian Honig is going to lead a discussion on in-kind contributions, and tomorrow is going to be in-kind day. There'll be quite a bit of presentations of the in-kind work there. And then on Thursday, Ohad is going to lead the discussion of road mapping, where we are and what further needs to be done. And then also, of course, the discussion sections can be used to resolve any other broadly interesting questions that could not be fully resolved, after each individual talk. Just a couple of other quick things. We do plan to have a group photo at some point. Maybe tomorrow we'll have the group photo. And so we'll try to make sure everyone gets a chance to participate in that. And then regarding the speakers, Gordon has already stressed that it's quite important for the speakers to keep to their assigned talk times, because many people will be coming in from many different time zones. And we want to be sure that if they come in at a certain time, they can get the material that they want to see. So we do have to be pretty strict about that. And so please, when the daily moderators, today Gordon, tells you you're running out of time, you do kind of have to wind things up pretty darn promptly then. we'll try to give you, say, a 3-minute warning, something like that, before your talk is over, so that you won't be surprised and it won't just suddenly come to an end. I would also ask that all speakers do send me, just by email, a copy of their slides. You can do this either just by emailing me the PDF file directly, if it's compact enough, or you can put it in a Dropbox link or an iCloud link or whatever works for you. And provided it's not too complicated, where I have to solve a complicated puzzle or something to get it, I'll download it, and that will be great. And then I will try to collect all those and make them available to everybody, for future reference. And so I think that's about everything for today. Those are my organizational points. If anyone has any questions, please speak up about those, and maybe if Gordon or if any of the other organizers have anything to add, that's great. Otherwise, we can get started.
Yeah, just to say that you can post questions in the Slack. I and the other organizers will try to monitor those and see if it's something that can wait till the end of the talk or needs to be interrupted. We do have plenty of time for questions, so that shouldn't be a problem. And then I made a Slack channel just on the LSSTC's Slack. So I did make it accessible outside of that of LSSTC, but I don't know what that means in terms of people actually getting access to it. But if somebody else knows how that works, and I put the channel in the chat. I would suggest using that for things that have sort of longer term value outside of the meeting, in the sense that we might not make the Zoom chat available. All right.
One other thing to add really quick, sorry. One other thing just very quickly. So the Zoom that we are currently running on is the Penn State Zoom. That's the main Zoom channel for the meeting. If somehow the internet conks out in central Pennsylvania, the backup Zoom is in the Zoom announcement. It's at Drexel that Gordon's running. So if somehow everything suddenly falls apart, you may get an email saying switch over to the Drexel one as a backup. Hopefully that won't happen, but I just want to make sure everyone's aware of that. Go ahead, Gordon, sorry.
Great, thanks, Niel. Okay, so the first official speaker is Will Clarkson, who has recently taken over from Federico Bianco as the overall chair of the LSSTC Science Collaborations. And he's going to review the status of the science collaborations and provide some insights for the Aegean Science Collaboration. Take it away, Will.
Thank you very much, Gordon. Thank you very much, Niel. Can folks hear me if I talk like this?
Yep, sound good to me.
Yep. Okay, wonderful. Thank you very much. All right, well, it's great to be here. Good to see everybody virtually over Zoom. As Gordon said, I've taken the position of Science Collaborations Coordinator less than 2 months ago. So I'll do my best to provide an accurate update with where things stand. And I'll finish with a few thoughts I think that are relevant for the Aegean Science Collaboration in particular, which I hope will be helpful. Quite a lot of what you're about to see, at least the sort of the slides about the collaboration, I should give credit to my predecessor, Federico Bianco. A lot of this is edited from a recent material that she prepared. So thank you, Federico, for this. Okay, so the Rubin Observatory Science Collaborations are, as I think you may know, these independent worldwide communities of scientists. And I think sort of a one-sentence summary would be that we are a federation of just over 2,000 scientists interested in LSST that the project listens to. And so in the context of maximizing what LSST does, we really have two roles to play. I think for the science community, the most important role is that we exist to help the scientific community prepare for Rubin science, and I'll say a few words about that later on. That can include preparing for what will happen when the data start to flow, so helping to form collaborations and working groups, to do the science for the decade of the survey. It can include helping the project configure itself in the best way to provide the data that we need as scientists. So how can LSST maximize the science for Aegean is one of the issues that the science collaborations exist to help with. And I think secondly, in terms of the project, listening to these science collaborations, formally the science collaborations do serve as a resource to the project. So the project has the right to ask the science collaborations for input on issues that may need help with. For example, input on survey strategy that I think Niel has already mentioned. For example, input on the in-kind collaboration, in-kind contributions, I think that Afrodita will talk about a bit later on in this meeting. And those two roles very much interact with each other. So, for example, in configuring the best way for the project, for the LSST survey to observe the sky and provide data, that's also very helpful to the science. And in turn, the science preparation is important for the input into how LSST will maximize its scientific productivity. So those two roles very much interact with each other. So a little bit about the science collaborations kind of globally, if you like. They all aspire to be an inclusive and supportive environment for scientists anywhere in the world who are interested in pursuing LSST-based science. There's no membership fees. There's no requirement to be affiliated in any organization. You could be just working by yourself, and you can join a collaboration. And there's no sort of top-level requirement for time commitment for basic membership. Although the individual science collaborations do have the right to set their own criteria for that. So the aim is to be inclusive. There are 8 science collaborations. You see them listed in the next slide. Currently covering 6 continents, 25 countries, a large number of affiliations, and altogether, as of March 2022, the science collaborations represented just over 2,000 scientists around the world. So this is a substantial collaboration, and that sort of scale can help advocate for things that the scientific community needs. So you can think of this, like I say, as a large collaboration of 2,000 people with the ear of the project, which is quite helpful. Just to show you a little bit about how this breaks down between the different science areas, you're seeing on the left the growth from 2018 in the dark bars to 2022 in the light bars of membership in the different science collaborations within the Federation of Science Collaborations. The figure on the right shows you the breakdown as a fraction of membership. So, for example, dark energy comprises just under half of the membership of the science collaborations. There's Aegean at the top, and you can see the different science areas represented here. Okay, so I think to illustrate sort of how the science collaborations help the scientific community, it is worth a bit of a look at the sort of the organization of how this works. So I apologize for the slightly busy slide here, but I think this does a nice job of explaining sort of how it helps. Focusing on the colored circles for a second, the science collaborations help each other by forming this sort of federated body of scientists with a wide variety of overlapping science interests, and it does that. The science collaborations pursue activities very much to help the science collaborations advance their own interests. One good example would be collaboration workshops between different science collaborations. And they can be organized around a scientific theme. They can be organized around sort of cross-cutting, if you like, technical themes. For example, observing strategy workshops that have been held for multiple science collaborations. And that all helps to kind of help us collaborate with each other and advance our science goals, and to learn, frankly, what others are working on, so you know which wheels you do or don't have to reinvent. One nice example of this actually is the work done by Gordon Richards and collaborators on differential atmospheric refraction, which is obviously vital for Aegean and turns out, of course, to be important for the astrometric performance of the observatory as well. So there's lots of other nice examples about this. So that's the science collaborations helping each other sort of develop the science areas. I think equally importantly, though, the science collaborations have excellent links with the project itself in a number of ways. Looking at the sort of grey ellipses at the top left of the figure for the moment, the project has assigned each science collaboration a liaison for different aspects of the project. The ones you see here, there's a commissioning liaison. Their job is to help the science collaborations provide input into what commissioning observations they need. There's a data management liaison for each collaboration. I think for many people here, that's important because questions like, what will LSST actually deliver to your collaboration is in there. The SCOC, I believe Niel mentioned that in his introduction, that's this committee that is working to understand sort of how to configure the LSST survey. They have a liaison to each of them as well. And then the science collaboration chairs meet with the project roughly once a month to help that communication go to the project. Within the science collaborations, there are also some sort of standing kind of cross-cutting committees. And the point of those is to help the science collaborations sort of set their sort of view and understand what's sort of going on these cross-cutting issues. For example, the in-kind contributions, that's the process that Niel talked about. I believe that Federico will mention tomorrow. The observing strategy, there's a advisory council for the LSST corporation. And then most recently, there's a new group that's been formed within the science collaborations, which is a diversity, equity and inclusion council. I'll speak a bit more about that if I have time later on. And finally, in terms of communication from us to the project, your friendly science collaboration coordinator has multiple hats and multiple channels available to help with this. That includes a seat on the Science Advisory Council, includes a seat on the LSST Executive Board, and so on and so forth. So there's a lot of stuff that we do, both to help the collaborations sort of scientifically improve their understanding, but also to communicate up and down from the community to the project, and from the project to the community. Okay, so a couple of examples about some of the output that we do. I mentioned before that we have one of the activities the science collaborations do is to hold sort of cross-collaboration workshops to help communication between different science areas. And that's already producing some interesting output. One example is this nice paper by Claudia Reiteri on blazar variability of interest to this collaboration. And a lot of the sort of connecting tissue between the different scientific areas has been sort of explored and developed in the paper as a result, I think, of these collaborative workshops and hack days that we were able to have. So this particular example includes authors whose primary membership are at least the four groups that you see here: Aegean, transients and variables, stars, Milky Way and local volume, and dark energy. Reaching back a bit further, the sort of collaborative output of the science collaborations goes all the way back actually to way back when the science collaborations existed to set the science agenda for LSST. And so on the slide here, you see listed some examples of this collaborative output to help the project sort of help the science. Way back from the LSST science book, which I think some people on this call contributed to, through the deep drilling field papers. I'm sure you'll hear about those during this meeting. And then most recently, quite a lot of the effort is focused on configuring the survey, the observing strategy, to provide the best science for the biggest number of science cases. And so on the left, you're seeing, for example, an authors network for the 48 white papers produced in this 2018 call for input on the configuration of the survey. And each of these sort of coloured discs represents an author from a different, or a group of authors from a different collaboration. And you can see how there's a natural kind of connection between different collaborations, all arguing that LSST should do this for their science. So the idea is that different collaborations kind of grow from collaboration with each other. We can all help each other advocate for the science that we need the project to produce. In terms of sort of metric output, if you like, output that could be useful for for example, publication metrics. One major recent initiative led by Federico Bianco is this AppJ supplement issue, focus issue on survey strategy optimization. And so far in that issue, which is still open, we're looking at about 8 papers published, 3 in review, and on the order of 5 we know of that are expected to be submitted to this. So it's not just white papers. The collaborations do help each other produce refereed published output as well. And I'll say a few more words about this if I have time a little bit later on today. Okay, couple of governance issues just for context for this audience. The 8 science collaborations have recently been federated into this federation of science collaborations I've been talking about. This slide is very busy, but you can read this, I suppose, after I've emailed it to Niel. But really a recognition of the efforts that science collaborations have given over the last, 15 to 20 years. The project is sort of supporting to some level the science collaborations themselves, and this gives in turn various rights and responsibilities. And so each of the 8 science collaborations has its own charter that allows the collaborations to sort of reflect the structure of what they want to do and reflect their own membership, all of which is under the overall charter for the entire federation. So I encourage interested people to look at the federation charter online if they wish to learn more about that. One thing I do wish to highlight, though, is this new diversity, equity and inclusion group, improving the ability of all scientists to participate in the process is such a key value to the science collaborations overall that the formation of a DEI council was specified in the Federation Charter for the science collaborations. That's now been formed and is starting to meet. One of our immediate tasks is to come up with a charter for this. But what it will do will include the items that you see on the left here. So it will include coordinating existing DEI efforts of each of the science collaborations. It will include providing a repository of things that have been tried and resources for DEI efforts, and to coordinate our efforts with the Rubin and Niel lab. So I'm showing on the screen here the different representatives to the DEI, this DEI council. Aegean representative is Matthew Temple, who I believe is on this call. But you'll notice that in addition to the science collaborations, there are representatives from Aura, Niel lab, and SLAC. So basically the operations, which shows you how seriously the organization is taking this.
3 minutes.
Okay, thank you. Okay, so let me show a couple of highlights then. You can read this in the slides. I'm almost out of time. But I would make the point that the science collaborations are sufficiently large and sufficiently diverse that sort of scale can be helpful in fundraising. I'll flash up one example, then I'll move on to the end here. And that's this grant that 3 of the science collaborations were able to raise from the Heisen Simons Foundation, the idea of which is to help prepare for science through this 1-year pilot study. And I think people in this collaboration may be interested to know that for the AppJS focus issue on Rubin survey strategy, I point out that part of this grant is set aside to pay publication costs, and that part's open for any science collaboration. So I do recommend that you contact Rachel Street, the director of this program, for more information. That's just to show you an example that the fact that we do have these big science collaborations can be helpful for raising funds. All right, since I'm almost out of time, I'll move to my final slide here, which is a few thoughts about how I think Aegean can sort of benefit from this federation of collaborations. As I said before, the Federation of Science Collaborations is a body of more than 2,000 scientists that the Rubin project listens to on various issues. So with that in mind, think about that as a resource to help you. I've written a few questions on the slide here that I recommend that Aegean members may want to think about. And I'll just flash through them, then I think I'll take questions. So, for example, I think you may want to consider what funding opportunities might be made available to large collaborations. And by large, I mean sort of groups of a few members from a few science collaborations that have common interests. That may open doors to fundraising that individual sort of small groups may not have. One important item I'd ask you to think about is: are there any missing items that you've identified that would help you write successful funding proposals, whether for your own group or as part of a big group, for LSST-related science? Shifting gears a little bit to sort of AGM in general, it would be nice to know what are still the biggest unknowns in terms of what LSST will actually deliver. What do you need to know before you know how well LSST will actually deliver for your science? And then finally, in terms of a resource for AGN, in terms of other collaborations to work with, are there any areas that AGN has been trying to start collaborations that, for whatever reason, hasn't taken off? Are there any collaboration areas that you want to start? Can we help in any way? Can the Science Collaborations Federation be helpful in helping make those connections? And finally, are there any science collaborations within the group that you already know that you want to increase connections with, and what would help that? So I must be over time by now. So I'll just finish by flashing up the link here to the science collaborations, and I want to thank you all for your attention. Thank you very much.
Great, thanks, Will. That was really useful. Questions from anybody? Either post them in the chat or just shout them out. So, Will, while people think, I mean, I guess I'll ask the obvious question to me, right, is, you mentioned there's no membership fees, but the Science Collaborations Chair is supported, at least at a minimum level, by LSSTC, which does have membership fees. And I'm curious to see if you could, speak to that relationship there, particularly in the light of lack of funding for LSST work. I mean, you ask, what are the missing things we need? I think the missing things are, NSF having any money at all. And particularly the fact that, LSSTC was once, intending to provide like users grants at the level of like $7 million a year. And that's why some of us got involved as members, and that clearly has, no longer a priority, right? And so that's a source of concern. Sure, and let me make a note of that, so I know to raise that later with LSSTC. Yes, the role of LSST has changed a little bit as the funding model for LSST has changed a little bit. So, in terms of whether LSSTC can offer these $10 order grants that you mentioned, I don't know what the status is of that. LSSTC does provide funding for a number of initiatives. As you know, there's the Enabling Science grants, which are
that's of order 10 to the $4, I think, and that's different every year. So that's worth looking out for products of that level. One of the areas in which I think LSSTC is very active is in its own search for external funding. For example, this LINK program and these Catalyst fellowships that you can read about on the LSSTC website, that is externally funded. So I don't really have a very clear answer to your question, because I don't know how LSSTC will develop over the next, at least at this point, I don't know how it'll develop over the next few years. But I do understand the issue that you raise.
Sure. Thanks, Will.
I don't know if that actually addresses your question. There's quite
I think it's a longer term discussion that we can have offline. So there's two questions in the chat. Matthew Temple wants to know the current status of Rubin Euclid joint DDPs and Rubin.
Yeah, thanks for the question, Matthew. I don't have the answer to that at my fingertips at this point. Can I get it back to you? I understand work is ongoing, but I have not looked into that in the last few days.
Sounds good. And then maybe one last question. Girish Kulkarni asked, is SC crosstalk also possible or allowed for in-kind contributions? That is it possible to contribute to more than one SC or to move contributions from one SC to another?
My understanding is that that's fine. I don't think there's any particular silo between the SCs in terms of one's membership when for in-kind contributions. Is that what you're asking about? The person who's asking.
Girish, you want to chime in or?
Yeah, thanks. I think that's part of the answer. I guess I was just a bit puzzled about all the discussion of, it appears that the scientific collaborations are very flexible when it comes to science, but they appear to be relatively inflexible when it comes to in-kind contributions, which could be for really genuine and justifiable reasons. But I just wanted to make sure whether that impression is correct.
I think it depends on the agreement between the science collaboration and the proposer, and it may depend on whether that happens before the award or after. But I see Sebastian has his hand up. Maybe Sebastian, maybe you can actually provide a better answer than I can.
Okay, I mean, just a quick note. This is a bit more than an informed guess, but where's the pitfall here? The pitfall is that when you provided your in-kind contribution, you essentially, one of the science collaborations normally signed off or accepted it as a contribution. And sometimes this has really just been one. So if you are tied to that science collaboration, then it's quite difficult unless another science collaboration says, oh yeah, actually we would be very happy to accept that and to move that over. And any such question should be raised with the in-kind contribution office, and then they will be raised with the coordinators in the science collaborations.
Thanks, Seb. We should move on. Thanks again to Will. Really appreciate you coming and joining us this morning, and look forward to productive conversations with you moving forward.
Yeah, thank you all. I'll stop sharing.
All right, Niel Brandt is going to present on the 2022 State of the Aegean Science Collaboration.
Okay, can people see everything okay?
Yes.
Great. Okay, so today I would like to review briefly the LSST Aegean Science Collaboration, focusing on its recent activities as of 2022, where we are hopefully just 2 years out from Rubin operations now. I would say that my overall impression while preparing this talk is that 2022 has actually been a quite busy year. And so I have a lot of stuff in this talk. I'll only be able to hit some of the recent highlights. My apologies in advance if your favorite activity is not covered in depth. And here I'm aiming to give all attendees, including new members of the Aegean Science Collaboration, a common broad understanding so that they can appreciate all of the relevant talks that are coming. So the overall goals of the Aegean Science Collaboration, of course, are to maximize the Aegean science return of LSST, to give feedback to the project to ensure excellent Aegean science, and then, of course, also to educate the broader community in terms of outreach and so on about Aegean science and the exciting work that's being done there with Rubin. We have just a very brief history. The Aegean Science Collaboration has existed since the fall of 2006. Here's an early email, I believe, from Michael Strauss when the science collaborations were first being set up. It has become more organized over time. Although, as we've already heard, the science collaborations have always been, by design, distinct from the project. You can go back to this early document from 2005, written by Steve Kahn. And that, of course, has made things challenging sometimes for making progress. But I think we've accomplished quite a bit, especially given the limited funding that we've had, at least here in the US. In terms of our current membership, well, we currently have 143 members in the Aegean Science Collaboration. According to my count, we grew by 36 members, or 25%, just over the past year, and that's been a regular trend, in fact, over the past couple of years. So we're growing rapidly. We have about 130, I believe, associate members, 13 full members, and the 5 largest national memberships are listed down here. Membership applications are welcome, even from people who lack data rights, but as we've heard, you don't get data rights simply by becoming a member of the Aegean Science Collaboration. There's this in-kind process for that. The application instructions are available on our webpage if you're interested. Also, as of 2019, we have an organized charter for the Aegean Science Collaboration. And as Will mentioned, we have received formal recognition under the new official Federation charter system for the science collaborations. Here's the overall organization. This is updated and adapted from the charter itself. There are 2 co-chairs, Gordon Richards and myself. Then there are a number of panels that perform important work ensuring that the collaboration is functioning, in a variety of critical technical ways. And then we have a number of scientific subgroups listed down here, things like Aegean selection, photometric redshifts, variability, follow-up, and so on. Then in addition to all of this, we also have our in-kind coordinators that participate and lead the in-kind process for the Aegean Science Collaboration. That's currently Sebastian Honig and Paulo Coppi. We have a liaison to the Critical Survey Cadence Optimization Committee. Franz Bauer is serving on that committee and acts as our liaison there. I'll say more about that later. And then we have also members of the Aegean Science Collaboration who are also members of this new Rubin Users Committee, which is charged with soliciting feedback from the community and recommending science-driven improvements to the data products and to the relevant tools. Qingling Ni and Ashley Villar are the current Aegean Science Collaboration members on this important committee. So that's the overall structure. What I'd like to do now is focus for a while on some recent and ongoing activities. First, I will just say briefly that we communicate with each other in a variety of ways. We have regular full Aegean Science Collaboration and subgroup telecons. We have, especially in recent years, had annual remote or in-person meetings. Here at the top is one of our few in-person meetings. This one was run by Ohad Shemer back in 2017 in Texas. And here at the bottom is the group photo from our meeting last year. We hope to take a similar photo this year. I think the meeting last year was very successful, and we're hoping the one this year will be comparably successful. We also have a valuable email list for communicating. We participate on the LSST community groups, and we have our Slack channels. So what I want to do now is talk about some of the work we've been doing. In particular, I'll start by saying that we've done quite a bit of work in gathering and analyzing key data for LSST and multi-wavelength studies of AGNs. One notable effort in that respect is the data challenge that has recently been done. It was kindly led by Gordon Richards and Beijing Yu. And this was, of course, part of our general efforts to prepare students, postdocs, and others for LSST Aegean science. 5 submissions were received. In this competitive data challenge. Monetary prizes were awarded, but the data challenge itself generated a very valuable data set, which we can use to prepare for LSST science. And that data challenge data set has been made public. I believe there's about 21 access requests in total, and Wei Zhang will review this further on Thursday morning. In addition, there is a draft paper being prepared on the data challenge results. Here is the author list and the abstract currently in preparation. This may still evolve some, but this is also being prepared. It will be a useful reference for members of the Aegean Science Collaboration. In addition, then, the Aegean Science Collaboration has been one of the leaders in fact gathering preparatory data for example, the deep drilling fields. Here is some nice work led by Mark Lacey, where he has conducted a very powerful survey called Spitzer Deep Drill, where he has obtained quite sensitive Spitzer coverage over the entirety of 3 of the Rubin deep drilling fields. And we'll be very happy to have these data in the can when Rubin switches on and all these data are flowing, and we'll be able to use the infrared data to get better redshifts, better characterization, and so on. We also have recently led an effort getting X-ray coverage for 3 of the deep drilling fields. About 5 million seconds of XMM Newton time was invested in these 3 deep drilling fields here in yellow. And here is the beautiful panoramic X-ray coverage all around the Chandra Deep Field South we have now. And we have now generated 10,200 AGNs, as well as many X-ray groups and clusters that will be extremely valuable. For example, when we have to finalize the best approaches to AGN selection. We have here a large ground truth X-ray validated sample of AGNs, which finds the obscured systems as well as the unobscured ones, and we'll be able to calibrate and optimize AGN selection for the full 18,000 square degrees based on data like these. People have also been working hard recently to utilize all the multi-wavelength data sets to characterize sources, for example, in the deep drilling fields. Fan Zhao has recently done X-ray to far infrared SED fitting for 2.8 million sources. This lets him separate out galaxies versus active galaxies versus bursting and quenching galaxies. And then one can also measure stellar masses and star formation rates down to fairly good depths. And this has led to a large public data release on Zenodo, which we hope will be useful to Aegean Science Collaboration members. I also want to mention that there's been an additional very valuable SED fitting effort for luminous sources in the XMM LSST drilling field led by Adam Marshall and colleagues. Here they have taken 711 luminous X-ray selected AGNs from this field, have done a good job characterizing luminosities, obscuration levels, emission line properties, and host galaxy stellar masses. And I think all of this multi-wavelength work is obviously going to be critical for AGNs given their fundamentally multi-wavelength nature. And you can see from this kind of timeline that as Rubin is switching on and the LSST is being performed, there of course will also be fantastic, very wide field data coming from radio surveys, from Euclid and Roman, and then there are X-ray data that are already available, quite sensitive for the whole sky. And putting all this together will be extremely valuable for optimizing AGN selection, understanding AGN, studying their host galaxies, and for a wide variety of other scientific topics. I now want to move on to our efforts on survey cadence optimization. You all know that there is this critically important survey cadence optimization process ongoing. Its goal is to determine how to observe the main survey best and how to spend about 10 to 20% of the time on the mini surveys like the deep drilling fields. This is clearly critical for a variety of AGN science cases. The Survey Cadence Optimization Committee has already released its phase 1 recommendations summary. I don't have time to go through these right now, but I strongly encourage you all to review those. That's very important. And they have also recently recommended a 5th deep drilling field, the Euclid Deep Field South, which will be observed, in fact, with 2 Rubin pointings at about half depth. So you'll have like 20 square degrees in this field, which surely will be well studied in the future. So we should probably, if anyone has spare time, start doing AGN selection and characterization in this important field as well. In terms of status and further needed steps, well, the Aegean Science Collaboration has delivered 8 cadence notes recently. Here are the abstracts for 6 of them. They're available at the website there at the bottom right. That give our recommendations for how the cadence can be optimized for AGN science. We've also, of course, have the 2018 white papers, and we've delivered, to my understanding, about 4 coded metrics that are fed into the operation simulations and describe which simulations are going to be good for Aegean science. There are also our two journal articles that are either published or ongoing. We heard about this one from the previous speaker on blazars, and there's also one being prepared on accretion disk reverberation mapping. And then additionally, of course, we communicate with the SCOC via meetings with Lynn Jones, and Franz Bauer is leading this important effort right now to collect in an organized way feedback from the Aegean Science Collaboration for the OpSim simulations. And Franz will be speaking about this this afternoon in the 45-minute discussion section that we have. It's also very important that we continue working through the operation simulations and to quantify as best we can and to prepare coded metrics that can be used to assess the simulations and tell which ones are going to be good for the Aegean science. And we should also continue constructively coordinating with other science collaborations to push for mutually acceptable cadence solutions. And we've had very valuable discussions in the past with the Dark Energy Science Collaboration in that respect. And then I will just wrap up, because I see time is probably getting short, with a few additional recent activities and some news. Of course, we have the roadmap. A new version of this is in progress on Overleaf. Ohad Shemer will report in detail on this in the next talk, so I won't cover it too much here, but I certainly encourage everyone to continue contributing to this very important effort. We also have, over the past year, prepared important PhotoZ letters of recommendation, trying to be sure that the overall broad photometric redshift effort for Rubin will include AGNs as best possible. And there are, again, 3 of these letters of recommendation on active galactic nuclei led by Roberto Assaf and Mara Salvato that will hopefully make sure that AGNs are treated in some fairly sensible way in the overall broad PhotoZ effort. As we've already heard, there is this in-kind contributions process. Tomorrow, we are going to have talks reviewing each of the in-kind contributions, where people can talk about what they've achieved so far. We can give feedback as to what would be much more valuable for us, and then we'll have time for discussion of this in the afternoon. So clearly, that's another very important thing. We'll hear a lot about that tomorrow. We also have connections with this new link effort, which is building this critical infrastructure to enable the large-scale science driven by the Rubin data. And a number of Aegean Science Collaboration members attended the recent LINK workshop and are helping to develop this community white paper on computational needs. And so that's clearly very valuable. And Nevin Kaplar, I believe, is now a LINK member, and hopefully he can serve as a liaison to the Aegean Science Collaboration in this respect. I also just want to mention that we have there are these Catalyst Fellows that have recently been announced in the recent Rubin Digest. We have one AGN person, Christopher Carroll, who won one of these LSST Catalyst Fellowships, and so hopefully that will give us further, energy in our science collaboration. Clearly, that's a great thing for us. And then in terms of other key activities, well, we have several members on the Rubin Euclid-derived data products working group. 15 Aegean science members are involved in Data Preview 0, and Vincenzo Petrecco will give us a talk later today reviewing that. And then we also, of course, continue to coordinate with other Aegean projects broadly, reverberation mapping efforts or X-ray observatories, to try to make sure that Rubin and these other things will fit together and give the best science for everyone. And then finally, I will mention that we also regularly give talks worldwide highlighting Aegean science. Here are a few of the presentations that the Aegean Science Collaboration has given in recent years. We certainly are happy to represent the Aegean Science Collaboration and Aegean science at institutes worldwide. If that would be valuable for some institute, we're happy to do that. We also have quite a bit of material now on YouTube. We have about 15 hours of science talks on YouTube from our 2020 and 2021 summer meetings. This meeting this year will add even more. And some of these are getting pretty good views. And so this is another way that interested scientists can learn about what we're up to, in an efficient way. And then finally, I will say that we also do a fair amount of work in outreach. I want to highlight this nice workshop on Aegean variability for students from Ethiopia and Serbia that some of our colleagues have recently run. Here is the link for that. Here in Pennsylvania, for example, we also run teacher workshops and talk quite a bit about Rubin and LSST and those. And then we present at other, local events and so on to highlight LSST, Aegean science, and talk about how it's exciting for the future. And with that, I will wrap up and thank you for your time.
Thanks, Neil. That's right on time. So we have plenty of time for questions, comments from everybody.
I see there are some things in the chat, but I haven't been reading it, so I can't tell if those are relevant or not.
I think those are related to Will's talk.
Okay.
So while people think, a comment is just that, the co-chairs and the panels of the Aegean Science Collaboration are meant to be elected.
Yep.
In practice, we haven't, had an election. I think I would argue because maybe we're slightly too underactive to justify that. But I guess, from my point of view, I don't know about yours, but, should there be people willing to step up, please make that known. That might make us more likely to have, to rotate leadership positions. For example, Niel's been the chair of the science collaboration for, as you saw, some 16 years now.
A long haul, yeah.
As opposed to desk, which is, sort of rotating every year. To the extent that Niel is, willing to keep doing this work for free, I'm happy to have him, keep doing that. But I think, both he and I and the other people sort of, leading these panels would be happy to give way should, should there be interest and willingness.
Yeah, I absolutely agree with those sentiments. And, we are building up the number of full members over time. And as more people become full members and so on, I think that's great if there is, healthy circulation in these respects. I think, as you said, it's been kind of a critical mass issue for a while. But I think, especially with the growth that we're having now, if you're growing by this percentage per year, I certainly hope these people who are joining because many of them want to actually be highly active, which is great. And if so, the number of full members will grow over time and we'll be able to start rotating these things. Yep.
Other questions, comments?
I guess we're good. So we can go to Ohad's talk if you like.
Okay.
Okay.
Sounds good.
Okay.
Thanks, Neil.
Yep.
And again, thanks to Neil's leadership over the years on this. Been really appreciated. Okay, Ohad, if you are ready, we can go ahead and get started with your presentation on the Science Collaborations Roadmap.
I'm ready. It's just that, is this the time to start, or do we need to wait a few more minutes for folks to come in?
I think we've got critical mass, and I would say let's go ahead and get started. We only have 10-minute breaks built in, so.
All right. Let me turn on my camera here. Okay, so can you all see the slide, Gordon?
Yes.
All right. Okay, so I will introduce the Aegean Science Collaboration Roadmap. Very briefly, this is an effort that we started off with support of the LSST Corporation back in 2016, even when we planned for a meeting, an open splinter meeting at the WS meeting in Grapevine, Texas, that took place on January 3rd, 2017. We've already seen this photo. So this is where we jump-started this effort, which took us roughly a year to get into version 1, which was eventually posted on January 24th, 2018. It was posted on, I think it's still posted on the SC website. Then over the next few years, we kind of consolidated. We worked hard to consolidate various standalone versions that were lying around on people's computers and also in various overleaf documents. So that effort, which was a bit tedious, was completed around April of this year. And then we decided that for this meeting, for this upcoming summer meeting, we'll have another version, version 3, completely on overleaf, no other standalone version. So there'll be just one document for all, and that is posted today. So let me just try to get into the link here. This is posted on the LSST website, and I know you're not seeing this, but let me share the screen again with the correct Safari page. So hopefully you can all see this now. And this is what I posted last night. Basically, this is the current roadmap of July 26, and also a link to, there's a URL here. We still need to polish this and make sure that there's only one link sitting here without this comment, but essentially you have a PDF version of this roadmap. And again, I hope everyone can see it. Again, polished and finalized. Can you all see this, Gordon?
Yeah, but Ohad, can I interrupt you for 1 second?
Sure.
The web page you're just showing, just so everybody's clear on this, has a login in the right-hand corner. That is for editing the web page. It's very, very confusing. Just want to make sure people are aware of that. But it is the web page that is basically put together for us by LSSTC. We are not in control of the format of the web page, just the content. And that people are confused by that every time that they look at it, and they think they need to log in to see,
sure,
to see anything.
Yeah, you're absolutely right. And again, it doesn't show my credentials up here, but we have two options. We have the actual PDF that was generated from the overleaf version, which can be linked to here. And again, I hope this would work. Again, needing some credentials the first time you log in. And again, you can see basically the same document with the list of authors and the contents. And this is, again, the most up-to-date version that I uploaded late last night. So it's all in here. So we could also link to that from the PowerPoint presentation that I will send over to Niel. So let me go back to my presentation now. And let's continue from here. So again, these two links will be here, and it will be posted on the Aegean website for future use. So let me get over here to the purpose of this document. First of all, the purpose of why we did that in the first place was to guide the Aegean science collaboration activities during the pre and post commissioning phases of LSST at Rubin. The idea was to identify and prioritize critical science collaboration, science goals, along with tentative timelines to achieving these goals. And also very important is to provide a reference source for projects that can be performed by groups and individuals across the community, particularly those pursuing funding support for such projects. So the idea, again, is to kind of look through this document, and I'll show you a few snapshots from it. And if you get into one of those sections and pick up a project or a bullet point saying, oh, we want to do follow-up observations or precursor observations of this and that field, you can form a group, form a team, and say, identify the actual number in the document, and then propose maybe a big project for a funding agency. So that's another important purpose of this document. So originally we had 3 chapters created by 3 working groups in 2017. Those are the Aegean selection, classification, characterization, Aegean redshift estimates, or the photoz's, and then Aegean variability science. A 4th chapter was added later on and was starting to be developed. There was a skeleton in version 2, and now there's a bit more to that, the Aegean ancillary data and follow-up programs, but it certainly still needs to be developed more. So again, if you're interested and if you're enthusiastic about ideas for follow-up programs or even precursor observations, please join or please contact the lead author of this chapter, Franz Bauer, for additional information and contribute to expanding on that chapter. So here it is, as we saw earlier on, through the links. This document is a living document, as I'll emphasize later on. It lives either on the Aegean website or on Overleaf if you have the link. And we can see just examples of the structure of this document. So we have now 4 chapters. Each chapter starts with the an overview. At the top, you can see the leading authors or the main authors of this chapter. But again, anyone can join in and contribute and be added to that. This is not a final list by any means. We have an overview and some background for the science to be discussed very briefly. Some chapters are heavier on the theory, some are less heavy, and that's totally fine. There's no formal structure to it. The idea is just to try and conform to the original chapters that were formed in 2017. This is the second chapter on photosys and variability science, chapter 4, the new chapter. And here's an example of a section from chapter 1 on the selection and identification, where each subsection is followed by a major Aegean science collaboration task ranked by decreasing priority. And again, these priorities may change over time. So this will be continuously edited. And for example, as I mentioned earlier, you could pick, say, bullet point 4 here and say, I'm going to work on section 132, bullet point 4, to determine the utility of folding into the selection algorithm, et cetera, et cetera, et cetera, and then try to connect with additional colleagues and form a group, form a team to propose observations or a funding proposal to an external funding agency. So this is, again, a very useful resource that we have at the end of every subsection. So let me talk a little bit more about the contents and what the roadmap is and what it isn't. So first of all, the good thing about it is that it's a living document. As you can see, it's not set in stone. It's still evolving, probably eternally evolving. The idea right now is not to publish it, formally publish it as a paper, but we can discuss this in the future if we need to. But the idea is nothing's final. Other chapters could be added, just like chapter 4. Some of the chapters still need to be developed, like chapter 4. But again, you can consider, for example, saying, hey, I think that chapters 2 and 1 should be consolidated into one big chapter. Okay, make an argument. We will, of course, discuss it within the roadmap community or the authors, the lead authors of the roadmap, and see what to do about it. It's a valuable resource to the Aegean community, just as I mentioned a few times. It can give you ideas for projects and proposals for funding agencies, and also to form collaborations with additional science collaborations, as Will earlier encouraged us to do. You can read the bullet points on this document and also look at other science collaboration roadmaps and try to forge new collaborations to work on mutual projects of interest. Now, again, what it's not a science paper. That's the idea. This is not a case where you say, oh, the roadmap said such and such in its theory or in its overview, and so I will quote it or cite it in my own paper. You better go to the references or to the citations in the roadmap and see what to do with them, not with the actual roadmap itself. It has no charts, no relationships, no correlations of any kind. It's just basically a memo for us about what we need to do in the future. And by the way, the fact that it's a living document also tells you that if we've already completed a task or two in the document, we can still leave it there, but we can say something, we can add something like, this has already been accomplished, see reference such and such, and now we're adding additional ideas to be written into. So again, not a full-blown, rigorous or comprehensive science paper, definitely not one of these things. Another thing that it is not a forum. So please, if you have arguments or you want to start conversations about content in the roadmap itself through Overleaf, which essentially provides you that option, is going to be very cluttered and very messy. I suggest that we all use these other channels like the Slack channel or the LSST community channel instead. Okay, so in terms of best practices, technically almost anyone that I'm aware of can edit an overleaf. And indeed, I saw over the past few weeks, many people coming in and editing and suggesting ideas, and that was great. However, because we're so many, Niel just mentioned earlier that we're almost 150 members, and maybe others from outside of the science collaboration might be able to log in as well. It's probably best to avoid clutter and avoid all this confusion inside the document, inside this overleaf. It's probably best if you just send your suggested edits and ideas directly to the chapter leads, who will consolidate those ideas into one uniform piece of text that could be copy pasted into overleaf. So again, these are the lists of the lead authors of the 4 chapters: Gordon, Roberto, Yanfei, Seb, and Franz for chapter 4. Now, general feedback can be sent to the editor. I look over the overall organization of the document. I check for consistency, that each chapter conforms to certain standards. I do the proofreading, polishing, and so on and so forth. A lot of tedious work. For example, again, if you suggest that 2 chapters should be merged into one, or one subsection could be eliminated in one chapter and moved to another chapter, and so on, please contact me at my email address. When suggesting edits, please fill out all the acronyms of the facilities, surveys, missions, etc., unless they were previously defined in the roadmap. This is a big problem when writing such documents. The document is littered with names of various surveys, various ideas for surveys. Some have been executed, some have not. Some are still being planned or will never come to be. So again, be very specific at what you mean with every acronym for every survey that you use. There are quite a few of these. So either add a reference or a URL to help the reader digest that better. And so whenever you do that, make sure you add a proper reference, and complete bibliographical information would be highly appreciated. So please use something like Smith J et al. 2022, the journal name and the volume page number, so the editor would not have to guess what it is, or send the bib info. I consolidated all these references, all this bibliographic information. Also have to comment out bibliography that is no longer needed, or that has been taken out by the lead authors. So just to summarize this brief intro of the roadmap, the roadmap again is a very valuable resource to the entire Aegean community, not even just the LSST community, but the Aegean community as a whole. The Aegean Science Collaboration members are encouraged to start working on projects outlined in those task sections. Again, the end of every section has a subsection of tasks ranked by decreasing priority. And again, it's not limited only to our science collaboration, but it can go across science collaborations. At least my goal is to align these releases of future roadmap versions with the annual meetings, like this summer meeting that we're holding today. So we'll have a timeline, a proper timeline, and not kind of stall for about 4 years as has happened between version 1 and version 2. Now, we do need to continue discussion about what we call this overleaf etiquette, who's going to come in and edit, how and what frequency, and where, because again, there's been a lot of this confusion, and there have been a lot of comments written with various font colors and so on. We need to see during the monthly Aegean telecon meetings who should go in and do that, when and how, and what's the best way to keep this overleaf document from continuing to serve as a valuable resource and a living document for the community. And I'll stop here.
Great, thanks, Ohad. Questions from those online?
I just had one quickly. So certainly, Ohad, thank you for the large amount of work you've done on this. Just to be absolutely clear, then, do you consider the current version, the current release as of today, to be like done and released, and we're kind of that is a successful achievement, and we're done with that version, and all further work will be toward the next version? Or is this current version going to evolve a little bit more in the coming weeks or anything?
Yes, great question. So yes, I consider this version of July 26 to be the final version 3 for now. And again, it's not by any means, it's not the end of the story for this roadmap. I'm sure there are typos or errors scattered throughout. It's a very large document. I made sure over the past few days, and I polished it thoroughly to make sure that there are no extra references, that all references are taken care of. I hope I have the right references for everything. I've reread it and proofread it multiple times. And so this is supposed to be considered the final version 3, and that's why the link on the Aegean website, on Science Collaboration website, has the July 26 name to it. Of course, it will continue to evolve until our next summer meeting.
Got it. Thank you.
Franz?
Just to highlight, it should evolve. It should be a living document, as the HUD was mentioning. One thing that is very much missing there is there's a large section of science that is completely unaddressed, right?
You mean the static science?
Correct.
Right. The static science was sitting there basically as a header, and there was not much development on it over the past few months, at least not that I'm aware of, on Overleaf. And so for now, it has been commented out. Again, nothing on the roadmap is eliminated. It's commented out until it is further developed. So for example, if we have things like TBD scattered throughout the document, I think I left a couple of TBDs because it was obvious that they should be TBDs for, particular survey that is still, we're still waiting on some results. But if a complete science topic is listed as TBD, it has been commented out for this version. And of course, everybody's encouraged to come in and edit it towards the next version of next year. So again, if we think another chapter needs to be added or needs to be uncommented, then I guess folks could contact me either during the monthly telecons or just offline, and we will develop it further. Certainly, this is an ongoing process. It's never the end of the story for the roadmap.
Yeah, and I think more than that would be, if anybody is interested in taking up, we could start a task force / working group on static science that would, like the follow-up, like the variability science, etc., sort of be in charge of developing that, because I think it is one thing that is lacking, even though I'm sure that we will all do non-variability science with Aegean, right? Yet there's nothing in the roadmap yet about it, other than the selection of them. And so, I encourage people here to think about what they could contribute to that particular section, and perhaps even volunteer to lead or help create that section.
Right. And again, I think that we have a session on Thursday to discuss road mapping in much more detail. We can start the discussion there. So again, the current 4 chapters are the one that were either quite mature from version 1 or just recently developed, like chapter 4, but we can certainly insert the Aegean static science or additional chapters that we think we should add. We can even suggest merging a couple of chapters like the photo-Zs with selection, if people see that this is a good way to move forward. But again, everything is flexible and still open for suggestions.
I guess, Franz, my comment on that was, I never saw the roadmap as having sections on variability science or static science. Like there was a section on Aegean variability, basically talking about things that needed to get done in order to do variability science. So I guess what I'm saying is I don't feel like a static science section is missing, right? So what tasks would you put there? For example,
that's up for the 60 people here to decide, right? In my opinion, for instance, do we have a control sample of non-Aegean? How do we get that? How do we have it basically a matched sample of Aegean that we can, understand Aegean activity versus non-activity? That would be one thing I would put there. right? And that's something that has a very large cross section with the galaxies SC, obviously.
Right. Okay, thanks. Rosanna?
I have a very simple question. Since this will be playing a role of living review in the sense, normally living reviews can be referred to in other scientific publications. But in other publications, can we refer to this in one way or another?
Excellent question. So normally this is not supposed to be, as I said, a comprehensive, rigorous science paper that one would go out and quote and say, whatever first author et al. In the roadmap said such and such, on page such and such, because again, everything that we say here is pretty much introductory material. It's not supposed to be a review paper on Aegean or Aegean science or even Aegean science with LSST. That's not the purpose. In fact, if anything, I would cite the other the other chapters that we've worked on and they're all listed here in the LSST science book 2009, and then all the Cadence papers that came later with Marshall et al, Phil Marshall et al, and then Bianco et al, the most recent one. If anything, I would cite those and or the original survey papers, such as the Niel et al work on the deep drilling fields, and other papers or other papers that are introducing new missions and new surveys that will come. I would prefer that over the roadmap because, again, this is not supposed to be that kind of quote unquote paper. It's just an internal document. It's a memo for us. And but again, this is all open to discussion. I know that Gordon is eager to publish this one way or the other, maybe providing it a DOI at some point. But right now, this is not, as we just heard through this discussion, it is not ready to be a published paper, if that answers your question. May have been too long, but the short answer was probably not.
Yeah, I mean, all had people who are trying, worldwide, who are trying to respond to their various grant agencies might want to be able to point at this, for the purpose of saying, well, I want to do this work, and this work has been endorsed as important by the Aegean Science Collaboration. And for that purpose, I think this document probably does serve a unique role. And if you consider version 3 to be stable, and I understand it's not going to be a published paper per se, but if you consider it to be, stable and good enough to have a DOI, that might help to make it citable. And I think colleagues worldwide who are trying to raise funding might appreciate such a thing.
Yes, and so there's probably an interim approach, and I totally understand that, of course. And again, it should be used as a resource to point out to funding agencies what you're going to work on. So you either take each and every bullet point here that you can see on the screen and turn it into an abstract and write upon that and just say this is endorsed or this is you don't even have to say that, because if you have a large group of, say, 20 researchers from Aegean or other science collaborations working on this bullet point, this is already strong enough. We don't necessarily have to say that this is a bullet point in a roadmap endorsed by a certain science collaboration. However, what you can do is you say, okay, here, this is bullet point 2 on section or subsection 1.26 in this URL. Now, I know that some funding agencies don't, they don't encourage you to include URLs, but you could do that. And since, again, this is a living document, that URL might change. The contents of that URL might change a year after. So we have to keep that take that into account. So I would probably suggest that interim approach rather than just stating it is the solid bullet point 2 in section 1.26, and therefore we're doing that, and this has been endorsed by the Aegean Science Collaboration. I think doing it this way that I propose is probably even stronger.
Thanks, Ohad. So one comment in the chat, I'll note Robert Nakuda suggested that Git might be better than Overleaf. I think you're not wrong there, but I might argue that everybody on this call could immediately start editing the Overleaf, whereas there's a barrier to using Git for some people. Usually the links that we've been giving for the Overleaf are the edit links. And so if you have the edit link, you can log in and edit directly. The track changes is set up by default So, in principle, you're not making a mess of things, but, as Ohad says, sort of be helpful to tread lightly and interact with the chapter leads.
Yeah, and here's what you can see on the track changes, by the way. You can see a lot of that going on. I cleaned it, by the way. I cleaned it yesterday from all the comments that had to be accepted or rejected, leaving just the discussions here. But again, it's best to keep those discussions out of overleaf and into the other community options that I mentioned. But again, the platform itself might change. Right now, it's overleaf. I think Gordon, you're the one who suggested that, and it's okay. But if we ever want to transfer it to another platform, that's totally fine. So having this as a solid document, as a solid science paper has its drawbacks. I think that keeping it as a living document, floating like this on one of these platforms is probably best at this point.
Great, thanks, Ohad.
Just one other thing very quickly. So thank you very much for all of this essentially volunteer work that you've kindly done, which is great. If you are able, if you consider now this to be an official release, this is version 3 and it's done. If you would be willing to turn this into, just a PDF file and say, as of today, send out an email to the Aegean Science Collaboration saying, as of today, version 3 has been released and here it is.
Yes.
Then people have like a permanent thing. Here is version 3.
Yep.
It's stable for what it is, and people can point at that as they need.
Yeah, and again, it's already on the Aegean website. Maybe if we have, Gordon, if we have one more minute, I'll just flip again to that link. So we will all have it on the screen now. Let me just show you that really quick. And if you can see that, I will likely remove this comment. I enabled that comment a couple of days ago, and I will likely turn it off again. But here it is. And we can send out another email to the collaboration announcing that. But here it is, the current roadmap. Version 1, by the way, is all the way at the bottom is first draft. This is what I consider to be the final version. That's the version you saw in Overleaf. And again, assuming no one else could accept or reject comments on Overleaf, then this version is stable and it's not going to change.
Great. That's great. Great. I think it's worth just circulating it to the science collaboration by email, but that's great. Thanks a lot, Ohad.
Yep.
Thanks, Ohad. I really appreciate the work there. So we should wrap up. We're at a break. So the talks so far this morning have been sort of infrastructure as a preview for what's coming. We're going to have 2 sort of pipeline talks and then 2 more science talks on reverberation mapping. We'll take a break now until 12:05 Eastern and start back promptly in, I guess, 11 minutes. Thanks, everyone. This is Yusra El-Sayed, who is giving us an update on the pipelines and data products. Yusra, take it away.
Thank you, Gordon. I'll leave my camera on as long as somebody else has their camera on too, because I don't like talking into a mirror. Thank you. Let me close my window. All right, so my name is Yusra El-Sayed. I'm the project manager for science pipelines within data management within project. And today I'm going to give you an update on where data management's been over the last year and where we are going. I'm speaking on behalf of the entire Science Pipelines team. We are scientists first. We are all members of a science collaboration. In grad school, I did pretty much only Aegean science, and I'm only a member of the Aegean Science Collaboration. And what we all have in common is that we thought that we can best contribute to the science of Rubin and LSST by working on the data products. The science pipelines take the raw images off the telescope, process them into processed images like coads, process visible images, aka calyx difference images, and catalogs like the object source table for source table. These images and catalogs will be distributed in two modes, fast and slow. Fast via the nightly alert stream, the prompt products, data products. These support science that requires rapid follow-up. Slow are the annual data release products. These support static science and statistical studies of variability. A misconception I hear all the time is that the difference imaging pipeline, which we call DIA, which stands for difference imaging analysis, will only be done during alert production. This is not true. Calibrated light curves are a data product of data releases as well. And the DIA pipeline is run during data release as well. We have a prototype pipeline in place, but we expect it to evolve over the next decade. This is because we are committed to providing state-of-the-art processing algorithms. And the state-of-the-art has changed a lot in the 10 years that I've been writing code for the pipelines, and we expect it to change a lot over the next 10 years as well. So the pipelines that are used for DR5 will not necessarily be the same pipelines that are used for DR1. Now, we do not have LSST cam data yet, and nor do we plan to have it for a while now. What do we do in the meantime? We use simulated data and data from precursor surveys. We use a big simulation run of IMSIM data from DESC's DC2 run 2.2i. This is good for cases where you need a truth catalog. This is not good, however, if you need the gory realities of real data, like ghosts and glints and satellite trails, which for those we use DCAM and HyperSuPrimeCam. DCAM is good because it does not have a atmospheric dispersion corrector, which makes it appropriate for testing the effects of DCR, the differential chromatic refraction. And HyperSuPrimeCam works well because it is as deep as we're expecting from LSST. We also have a new precursor data set. Oxtel is in operation. Rubin Observatory is taking data with it now. However, it's only one small chip. And while not good for wide field precursor studies, it is good for testing the effects of how well the instrument signature removal is working. So anybody who works on instrument signature removal has been using Oxtel because it's a real LSST chip. We've used the pipelines in major data releases using these precursor data sets. So the LSST science pipelines are the HSC pipelines, and we've done some public data releases with these. I know in this meeting in years past, there have been some sessions on the Aegean science that were done with the HSC data releases. We are currently working on the fourth and final public data release for HSC, something that has, so between PDR3 and PDR4, we have written the Gen 3 DIA, the difference imaging analysis pipeline for data release production. And now most of the HSC survey strategy is not really appropriate for variability studies. You take a bunch of observations of one part of the sky, and then you move on to the next part of the sky and the next part of the sky, and you don't return back to the same part of the sky on multiple days. With the exception of the deep, ultra deep field over Cosmos, where we have hundreds of visits that cover the same part of the sky. And if you are in the HSC science collaborations, now is the time to make some noise about wanting to run the DIA pipeline on Cosmos for the next and final HSC data release, because I think it's still being discussed. The other data set that we've been using for major data releases is IMSIM. We've done 2 data releases with IMSIM data before yet. One was based on the science pipelines of a few years ago. This was processed by desk and turned into data preview 0.1. We recently reprocessed the same data set on the cloud using the version of the science pipelines from last fall. And this is called DP 0.2. And I understand that Vincenzo is going to be talking about DP 0.2 in more detail, and I was excited to see that so many of you are delegates. These data previews are the first in a series of data previews before DR1. These are driven by the project timeline. Now, I know the dates, the dates keep shifting and they have very large error bars. The project has recommitted to keeping a website with these major dates updated. And if you're ever wondering when ComCam is going on Sky, go to this website for the latest. But this timeline is going to be what's driving the data release schedule over the next few years. We have ComCam on in Chile now, but you can't start observing until you have the mirrors on the telescope. That won't be until next spring. And once we start first the survey with ComCam, we'll start collecting data for data preview 1. So here's the data products. Each data preview and each data release, we expect more data products to be tested and released as part of them. So in DP 0.1, for example, we had object tables and source tables. In DP 0.2, we added the DIA pipeline and now have forced sources and forced source on DIA objects and difference images. For DP1, we plan on running the prompt processing pipeline as well in canned mode. Now, what that means is because you need templates to do real-time difference imaging, we will collect all the data, create the templates during this data release production phase, and then use those templates to run the processing, the prompt processing pipeline. And we'll distribute alerts. However, they will not be in real time and there will be nothing to follow up in real time. Then using the templates generated from DP1 using ComCam data, we will try you doing live brokered alerts for the first time with LSST Cam DP2. And that will be roughly, so we expect LSST Cam to go on in February of 2024, and then do a 4-month mini survey with that. And then the data release from that will take another 6 to 9 months. So this is the schedule for data previews and data releases to keep an eye out for. And right now we are here. So I'm not gonna spoil the next talk, but the data preview 0.2 is out. There's a notebook aspect, a portal aspect that are available. Even if you are not a delegate, you can still access the schema as part of the schema browser at this website. The light curves you can find in forced source. So forced source has the object, it's the object centroids forced photometered on both the calyx and the difference images. We kept that separate from forced source on DIA object, which are the DIA object centroids forced photometered on both the calyx and difference images. The baseline plan is to combine those into one table called forced source. But this is one of the things that we wanted feedback from you folks about, is whether it is okay to keep these, and preferable to keep these as 2 separate tables going forward. But for example, this table has the object ID and then also the PSF flux as forced on the difference image and the PSF flux as forced on the calyx or the processes image. Okay, in terms of plans for the science pipelines, if you did not attend the algorithms workshop or haven't seen these videos, I highly recommend them because they are still very much current in terms of what we plan to do. Nothing has changed here. For status, that is where the algorithms stand now. I'm happy to answer if anybody has specific questions about astrometry or PSF modeling or whatever, happy to answer those now. I did not think that we had enough time to go through all the updates for the last year. However, I invite you to a 90-minute session at the PCW Wednesday at 11 a.m. This will be in a remote enabled room, and please join. Sophie Reed is on Thursday running a session on synthetic source injection, and she's hoping to have, I know she got some Aegean models from Matthew Temple and is hoping to have some results to show from those Aegean being injected into HSC data, I think, on that day. So please come to that as well. The source of truth for the data products is this document called the DPDD. I know some of you have it memorized. I know some of you have not opened it at all. If I'm offering if you want to go through this in more detail, I'm offering a longer talk on just the data products at one of the regular science collaboration meetings. And I'm also your data management liaison, which means that I collect and monitor your requests for features that aren't explicitly called out in the DPDD. Now, some of these are just implementation details that were just too fine-grained and detailed to mention in that document. So for example, doing force photometry on the template to use as the light curve 0 point. So this is already planned and written down in the baseline and on our to-do list, but did not get in by the pipeline freeze for DP 0.2. We have, if you are really missing it, we can, I think, complain and spend some more cloud bucks to get those run now. Hint, hint. And other things that I'm monitoring are the desire to have a list of known AGN to monitor during alert production in case they do something that's not a 5 sigma event, but something that requires something that warrants rapid follow-up. There's also the ensuring sufficient breadcrumbs for DCR when we finally implement the chromatic PSF models. Keeping around lossy compressed process visit images from alert production, and the issue of the report that we heard that star galaxy separation was difficult for point sources that were variable and no longer matched the COAD PSF model. And of course, whatever you are worried about, that is why I'm here. I asked around what folks in DM wanted me to tell you at this point in time. Robert Lupton wanted me to tell you that you should not get your hopes up for sub% U-band photometry, that the chips are not, the CCDs are not as good as we were expecting, and that he's confident we can get to 5% U-band photometry, and eventually 2%, but that won't be right off the bat, and definitely not 0.5%. And yeah, and then finally that DP0.2 is still in development, and don't expect a fully fledged set of services or data products. And this is an exercise for both project and community to work together to ensure that we are ready for DR1. And that is it. Thank you.
Great, thank you. So there's two questions in the chat. Maurizio asks, could additional data such as VST Cosmos, where we have multiple epochs, be suitable for additional testing?
Hang on. Sorry, Cosmos, from which telescope? Via VST Cosmos.
Yeah.
Sure. By whom and with what hardware? And
Maurizio, you want to unmute and just ask?
Yes, I'm sorry, I'm in an airport, so the connection is also. Just we have multiple observations taken over several seasons over the last 10 years with the VST telescope, in which single epochs are similar to single epoch Rubin observations. So we were wondering, we had been trying to see if we could ingest them somehow, but we were wondering if that could be actually of interest to test the difference image pipeline at some point.
Okay, well, thank you. We can look into using it for testing. It's I don't think it won't be possible to do like a formal data preview with it. But yeah, like we can definitely use it for testing.
Mara?
Yes, hi. I just realized that I probably misunderstood. Am I correct that you are saying that for the objects that are, for measuring the variability of the object, you are fitting every time with a PSF model, and then you see whether there is a difference in the residual? Right? I think that is what you were mentioning. Because in the slides that you were showing was like model PSF. And so I was trying to understand exactly how the procedure was. And maybe if you could spend a word more on that. And then I have another question.
Okay, so light curves. For light curves, you don't want to take the single epoch detections and measurements and just match them. The reason for that is that you're missing you're missing the epochs in which they are the faintest, and your estimates are going to be biased. Right. So what we do is we use deep coads for detection. Those the centroids of the objects that are measured on the deep coads, and the union of the DIA sources, which is we call a DIA object. So we take all the 5 sigma detections on the difference images, and then take the union of those, and those become DIA objects. So for the centroids of objects and DIA objects both, we then go back to the CalExps, the process visit images, those are the single visit images, and the difference images.
Okay.
And we measure the PSF flux at those centroids on both those sets of single epoch images.
Okay, then I will have understood. Perfect, thank you. I have another question, but I put it on the chat. The other question that for me is important is when you are saying that the moment you are testing on hypersuper CAM data and the CAM data, are you also implying that the format of the catalog will be the same for the normal galaxies? Are you going providing aperture photometry or total flux? Because this is something that I do not know. I promise I will read the document that you were pointing out, but at the moment I didn't do it. So if you can answer, that would be great.
Sure. Okay. So galaxies, where is it? So for colors, for galaxies on the object table, we are recommending the HOP fluxes. This is a PSF matched aperture flux. There's also plain circular aperture photometry. There is a what we call C model flux. Now, for galaxy photometry, for total fluxes, this is something that is likely going to change before DR1. We are pursuing codes that DES uses, like ngmix for that. And is there anything that I missed in your question?
So the gap is the same as the kids survey as used, if I understand correctly, is the Gaussian dingy. And my question is how many apertures? So 0.5, 1.5, 2.5, and 3. So you're giving 4 apertures.
That's right.
Okay.
And yes, and we can compute more. These were the ones that we thought were most useful to test out for DP 0.2. So if you have suggestions on different apertures, please let us know.
The point is that I'm asking for is that normally for pencil beam surveys where you have the lack of nearby objects, 3 a second or 4 a second are sufficient because essentially all your object is included in that aperture. But because we are going to be essentially all sky, you are going to have hundreds, thousands of nearby objects where the total flux of the object is not going to be included in 4 a seconds. And so when we are going to compute photosis for these objects, we are going to have an issue.
So let me suggest we move it to the Slack.
Yeah, sorry.
And then, no problem. Franz, something really quick before we move on?
Yeah, just that we've been trying to basically run the pipeline on DECChem data, and Demetra has lost a significant fraction of her life to doing that. Is there any help you can give us in that regard to make that an easier task?
Yes, yeah.
As our liaison?
Yes, of course, I would be happy to.
Okay, thanks.
Yeah, I know the DIA pipeline does work. We use it internally for testing the DIA.
Yeah, we're not even, we're nowhere close to DIA. We're in the ingest and photometry phase.
Okay, yes, hit me up on Slack and we will help.
Okay, thanks.
Great. Thanks, Yusra. Really appreciate this. I imagine there's going to be some questions, including myself, that maybe we can post in the chat and sort of have a longer term discussion. All right, so we're going to move on to Vincenzo Petrecca, talking about the LSST data previews, the current status relevant to the Aegean, and a brief tutorial of the Rubin Science Platform, which may lead to some questions that are relevant to the previous talk as well.
Okay, can you hear me?
Yes.
Okay, so first of all, thank you for giving me the opportunity to give this presentation. Today, I'm going to talk about the LSST data previews with a brief tutorial of the Rubin Science Platform for what is relevant to the Aegean science collaboration. So let's start with a summary of the data previews. This one was actually been showed before by Yusra, and I think that I have an older version of the document here because the release dates are different. But what is correct is the different data products associated with each different data previews and with the final data releases. So before the first data release, which I think should be at the end of 2025, we will have 3 different data previews. And with this talk, I'm just going to focus on DP0. And the first aim of DP0 is to serve as an early integration test of both the LSST science pipeline and the Rubin Science Platform, which is somehow where the data will be distributed to the final users. And to do so, a limited number of students and scientists have been given access to both the data and the Rubin Science Platform. They are known as delegates. There are 600 of them up to now, and the first half gained data rights during the release of DP 0.1 last year, and the second half less than 1 month ago with DP 0.2. And the main difference between the 2 data releases, the two data previews, is that DP 0.1 is mainly focused on static science, while for DP 0.2, there's been a reprocessing of the entire dataset with the addition of the time domain part with the difference images, analysis, the DIA sources and full sources, as Yusra told us before. So let's quickly talk about the dataset. It consists of 300 square degrees of simulated 5 years of wide fast deep survey mode. This simulation is based on the data challenge do made by the Dark Energy Science Collaboration, and the adopted baseline is this one, which was the fiducial baseline at the time the simulation has been done, and I think it's not so different from the actual one. There are plenty of sources included, galaxies, Equinix supernova and stars, with a fraction of them variable, but there are also not included sources, and here it is important to stress that Aegean are not included in DP0. This is one of the first and the biggest issue that we have as a science collaboration, because we cannot do tests using the sources we are interested in. So the issue is that we lack a comprehensive task data set for Aegean studies, and for comprehensive, I mean a complete simulation of Aegean observed in the LSST survey and processed with the LSST pipeline. And I am highlighting these two words because we need both of them in principle. We need both to assess what we can do with the exact LSST observing condition, and we need to understand what are the limitations of the LSST pipeline for our science cases. And to do so, there is a simulation that is it has been programming, and you can see more information about it with talk by Angela Bajorlo about Italian Kant contribution. This is a good thing, but there's a problem. It will require some time, so it is not something that we will have like tomorrow, but as the survey is approaching, and it is really approaching, we need to do something in short time. So here's a couple of points that we could discuss later about it. The first thing is that we can try to see if there's any possibility to collaborate between the EGNSC and DESC to release the simulated deep drilling field of DC2, which contains Aegean and all the sources which were not included in the wide fast deep simulation. This is not yet included in DP0, and I think it's not yet publicly available. Maybe they are going to release this simulation, but we need to understand how and when, and if you can use it for our test. And another thing that was mentioned before by Franz Bauer is the ingestion of archival dataset on the Rubin Science platform or something similar for further tests, because to ingest and process data, you need an observation package to process the data with the LSST pipeline. And there are such packages for the SpinCam and for TCAM. I'm not sure if there is one for the SDSS, but this could be a possible expansion of the Aegean data challenge. You can see this talk Wednesday about it, because for the Aegean data challenge, we just used SDSS data for the optical variability part, and we were trying to mimic what the final LSST data products are, but data were not processed with the pipeline. So we did not have, for example, difference image analysis, and this was a limitation. The data releases, including DP0 and all the data previews, are going to be released through the Rubin Science platform. It is an environment from which users can access and manipulate all the Rubin data on the same machine where the data resides. So this is the next to the data paradigm. You don't have to download tons of data on your local machine. You can just use this platform. This is the main page of the platform. It has 3 different aspects. The notebook aspect, it provides Python-based access to the data using a Jupyter Lab environment. Then there is the portal aspect with a graphical user interface, and it is very useful if you want to do queries and just visualize the data without using Python. And finally, there is an API aspect that enables to access the data using the virtual observatory interfaces. For example, you can use TopCat to visualize the data, which is something very useful. So if you are interested in understanding more about the RSP, I am referring to this talk by the young guy. It is 1-hour talk that goes really into details of all the different aspects of the Rubin Science platform. The RSP is also arising another issue that maybe is not so a big issue as the first one. It's just something that we should talk about, because maybe not all the people within the AGNSC know the answers of this problem. We know that the The Rubin data management system will provide at least 10% of total capacity for user processing and storage. And we also know that the RSP will run at the Rubin Observatory data access centers. At the moment, it is running on the interim data facility, I think hosted by Google, but it is something that is going to change. In this map, you can see all the operation sites. There is also one in Europe and French. There should be one in UK, I think, that it is not present on this image. One of the problems about the RSP is that there are no GPU resources at the moment. And I don't know if this is going to change in the future, but this could be a problem for example, for deep learning algorithm. And many of them have also been proposed as solution for the Aegean data challenge. So this means that we cannot use the RSP to test such algorithm. Another thing is about creating a Rubin independent data access center. There is this document here explaining all the policy to make these IDACs. And I know it is also something related to different in-kind contributions for various countries, but the question here is, do we have IDACs specifically for the Aegean science collaboration? I mean, we are preparing a lot of simulation, a lot of software as in-kind, but do we have a plan on how to distribute this data and how to run our software? So maybe this is something that we can discuss tomorrow, as it is the in-kind day of this Aegean meeting. So at the moment, it seems that I was just telling you about what is bad with DP0, but there is also room for opportunities, because even if there are no Aegean, the technical aspect is very similar for different science cases. And I won't try to convince you showing an example with supernovae that has been done within the Rubin Science platform. So at a beginner level, what you can do is just look at the catalogs, retrieve light curves, and make simple statistics on time series. At a more intermediate level, you can merge multiple tables together. For example, you can look at both the DI source tables with variable object and the object table with the static science, and you can try to inspect the surrounding of the transient looking at the images. And you can write your own Python scripts and launch them on the Rubin Science platform. For example, here I retrieved some estimation of the photometric redshift of galaxies, and I am trying to associate each supernova to the correct host galaxy. And I'm ranking galaxies according to a certain score that I am associating to them. And this is possible to do within the Rubin Science platform. An even more advanced thing is that you can put all together, and you can also use external tools within the RSP. And if it is something that can be installed with a simple pip install, like this software here by Nana, you can put it into the RSP. And for example, here I'm doing classification using templates of light curves for supernovae. All this workflow is possible within the RSP without downloading a single megabyte on your local machine. And it is something awesome. Something that it is, I think, more related to Aegean is the problem of testing the DIA. So this is something that there is discussion ongoing on the community forum. I also saw a reply by Yusra yesterday. I'm sorry if I haven't replied yet. The problem seemed to be solved, but what I want to show you here is that you can use supernovae or other sources to test for problems that you may expect with this pipeline. For example, I retrieved the light curve using the flux measured on the difference imaging for a supernova, and you can see that there is variability also outside the peak of the supernova. This is something not physical. There is this offset here for the I band, and if you look on the images, you can see that the problem is related to the supernova present on the template image. So the supernova is not present here on the single CalExp, but you see this negative variation of the difference image. And this is something that you don't have on the other bands, like here, the R band. Supernova is only present on one of the images, and you see the positive variation. So I am trying to see if there are more complicated objects, to see if there's problem with the blending. And another thing that we can do is trying to simulate objects at the center of galaxies and run the difference imaging task to see how the flux measured on the difference images relates to the total flux measured on the same image. Because we know that there is the problem of the changing template between different data releases. There is this document here. Don't worry about the links, I will release the slides. And there's the possible solution to solve this problem, which should be something like measuring the difference between the templates and adding these components to reduce the offset. Is this going to work? I don't know. Maybe we should test it. And it is a problem, and it is better to face it before the data release of the survey. Last but not least, another user case is the possibility to query external catalogs within the Rubin SES platform. So to be honest, it is something that I haven't gotten into details yet. This is a screenshot from the portal aspect of the RSP, and you see that there's possibility to select different catalogs which are already present in the platform, but there are also people working on the possibility to ingest other catalogs. And so you can here make a simple query using coordinates and see what happens. And it is very important for multi-wavelength studies. So within this jungle full of things, the first question, I think, is how to get started. So here I try to help you. These are linked to official tutorials. This is the official documentation for DP 0.2. This is the GitHub repository. And if you are a delegate, this is already cloned on your notebook aspect of the RSP. These are YouTube recordings. You just go to the Rubin Observatory official channel and look for videos starting from DP 0.1 or DP 0.2. I think there are at least 20 hours of video, so it is a very useful source of information. Then there are the DP0 delegate assemblies bi-weekly on Fridays, and this is the Zoom channel. But the most important thing is just to ask people that you know that are working on this thing. So that's why I would like you to join the TBS DP0 task force if you are interested, because as I was saying, the technical part is very similar for different science cases. So this is a community. We have our monthly telecon, and we just discuss a problem that we have with the RSP and how to solve these problems. These are the main preliminary results. We were working on the preparation of short tutorials on specific objects like how to produce a light curve and so on. There are people working on this. I told you that I was not so into this problem, but there are people working on this. And we are also trying to work on the possibility to inject fake sources into the images. There's been a presentation by Jeff Carlin of a tutorial notebook, and we are trying to make things more complicated, simulating objects within the galaxies. So you can just join this channel or ask the chair, Sarah Bonito, or me as a co-chair if you have other information. So just to summarize, take-home messages is that we have some limitation. And the biggest one is this, lack of a test data set. But there are also opportunities because there's plenty of tutorial to learn how to handle the data products. Plus, there is a big community, and it is better to learn now than later when you have to rush because you have the data release and all the other things. So I think it is still important to work on DP0, and maybe we should create a sort of task force and put something into the agenda for our monthly telecon about DP0. I don't know how much time I get. I also would like to show you a brief tutorial of the RSP of both the notebook and portal aspect.
Yeah, you have 3 minutes.
Okay, I will be fast. So this is what you have when you log in. If you click on notebook aspect, you will end up at something like this. If you go to notebook, you will have, if you are a delegate, the tutorial notebook repository with all the tutorials already present. You can just click on it and run. I have prepared a small tutorial. Don't worry if I'm not able to show everything now, but this notebook is going to be released formally as a DP0 delegate contribution. So there will be probably in September during one of the DP0 assembly presentation, and I will also present this during the TBS DP0 task force. So in this notebook, I will explain how to extract light curve and how to get the images of the cutouts of the template, the collects, and the different images. So this is the import of the main packages, some function to remove figures to save some space. This is to produce cutouts. So I want to say that all the information in this notebook is possible because of the tutorial notebooks that are very useful. So you can just copy and paste and just little modification of what you can do. I will just move to this part, which is the query part. You can use the tab service with the ADQL language. If you're not familiar with it, it is basically select with the information that you want, and you can retrieve this information about the catalogs looking at the schema browser that user showed you before. Then there is a from where you select the table, and on where we store the conditions. So here I'm just querying the truth table, and I'm looking for supernova, truth type equals 3, with redshift minor than 0.3. I am getting the results as a pandas data frame. Then I am exploring the result. I'm just selecting one object. For example, I'm selecting this one with no offset, just to show something with no problems. You can get the coordinates using AstroPy. You can also get the track and patch if you need to get the images. Then there is another query to the DIA object catalog to get basically the object ID, which is the unique identifier of the object. Once you get this ID, you can go to the DIA source table to retrieve all the information to build the light curve. And I am retrieving PS flags and the related error, which is the PSF photometry flags on the different images. And I am also getting the total flags on the direct image. And this is to have magnitude, because by default you have fluxes in nanojansky. Here I am defining masks to separate the different bands. And there's the possibility to make the plot with all the point. This is in flux, but you can also have it in magnitude, because I have magnitude. I will just go rapidly to the image production. We'll skip this part. Okay, we'll go here. So to get the image, I also queried this ID, CCD visit ID, and the last three numbers of this ID are for the CCD, while the first numbers are for the visit. So I am splitting the visit and the detector. So you use the butler to get the image. You just select the dataset type, and as a data ID, you put the visit and detector, and you can get the collects with this line of code here. You can also get the defects and the template, and then there is a procedure here to plot the images. And as you can see here, there's no supernova on the template. Then on one image, I have something here. This is less deep than this because this is a cohort. And on the difference, you are seeing this point here, which is your supernova. All the things that you can do here are also possible within the portal aspect, which is this one. Here you have this graphical user interface. You can just put the coordinates. You can just select what you're interested in here. Here you select the table. And you can also use this with the ADQL like query. That was the language that I was using in the notebook. So you can do more complicated things, but with this graphical user interface. So that's all for today. If you have a question, I'm happy to answer you.
Thanks, Vincenzo. Yeah, we should take a few minutes for questions. Well, while people think, one quick question that I was going to ask either you and or Yusra, what's the best way for people in the Aegean science collaboration to sort of get used to, data that's not SDSS data? And it may be that you just answered that, in the sense of like pulling out all the supernova light curves and just treating them as okay, these are Aegean candidates, what does your code, do with those, right? And can you, identify them as things that aren't Aegeans? I mean, does that make sense for people, right? In terms of getting used to the DIA sources and objects?
I think actually, if they're nuclear supernova, that's the best, right? Because those actually will look more like Aegean.
Yeah, that's the point. And actually what I am doing now is to look at all the supernovae to find the nuclear ones, because I was just randomly looking at 5 supernovae and they are not nuclear. So I think that there should be nuclear supernova. That will be very interesting.
Yeah, great. Maurizio?
I think there is an additional problem that Aegean can be, bright in the template and dimmer later. So you will have these negative objects that the supernova will not simulate.
Yeah, another possible option would be to mix up the time component, but that probably you would see too strong variability. But you could at least use that to stimulate some different type of variability from just a supernova that goes up and down.
Yes, another idea is just to simulate sources, fake sources at the center of galaxies.
Yeah, yes, right.
And you can still test for purity. You can look for Aegean in the light curves in the force source and force source on DIA object tables and make sure that you don't find any.
Great, thanks everyone. We should probably move on. Franz, quick question.
Just, I guess there's no deblend. I mean, so the deblending is basically an afterburner sort of thing, or will DM be providing deblending information?
There is the deblender was run on the coads, and so anything in the object table is the children. If you use the detect is primary flag, if it's true, then you're looking at one of the children. If it's false, you're probably looking at one of the parents. But it's the deblender info is all in the is in the object table. There's no, but not yeah, I don't know if that answers your question.
Yeah, no, I guess maybe we probably want to think about doing some sort of forced nuclear deblender, and that may, I guess, be an afterburner thing that we do, because we want to basically assess the flux of a point source in the center of a galaxy, right? And so you'll have the variability component of that, but you'll have the static component as well, and that's going to be a little bit tricky, I guess.
Let's take this to Slack. All right, we should move on. The next speaker is Yaseman Homayuni, talking about the census of black hole accretion structure and mass with Rubin LSST. If you're ready, you can go ahead and share slides.
Start sharing. Can you see my slides up?
Yes.
Okay, perfect. Hi, everybody. Thanks for the opportunity to give one of the science talks here. So today I want to talk about the census of black hole mass and accretion disk with Rubin LSST. So despite decades of research, we still lack a coherent picture of what are the main physical drivers of black hole growth. And that is, what is the role of large-scale environment on fueling the black hole, and what is the impact of the black hole-driven outflows on the growth of galaxies, and really how do these two evolve over time. So in order to study that, one of the main limitations here is that when we look at the black hole mass versus galaxy stellar mass, much of it is limited by the large uncertainty on the black hole mass measurement, which in this case spans about order of magnitude. So how do we do a better job of getting this mass measurement? So the black hole itself, the sphere of influence, is very tiny. It's spatially unresolved in most galaxies. For local galaxies, it's possible to map dynamical effects, and we cannot really directly probe the structure of the matter as they fall into the black hole. Of course, there are a few exceptions here. There is the case of the first quasar 3C2783 and also NGC 3783, where the gravity team were able to resolve the structure of the rapidly moving gas around these supermassive black holes. And this was the first time this so-called broadline region was resolved. And more serendipitous observations are the ones from EHT team, where the Sagittarius star and also M87 were observed through practically using Earth as a massive interferometer to get the shadow of the black hole and study so many things about the black hole themselves. But if we can only do this for a very few number of supermassive black holes, how do we expand our understanding beyond this? So here comes the reverberation mapping technique, also known as echo mapping technique, which is the only available tool beyond 100 megaparsecs. The quasar environment is prone to rapid short-term changes in ionizing flux, which results in the variability of the quasar light. And this variability gets echoed or reverberates from different components, and different components respond in a different way, where the high energy emission responds in lower energy emission after some time delay. And you can see this in a little movie here, where we have the emission from the accretion disk getting reprocessed by, in this case, the dusty torus, and then you can see a time delay between the two. So as one of the main components of a supermassive black hole, the broadline region response is changing continuum flux after some light travel time. So in principle, what reverberation mapping does is that it substitutes temporal resolution rather than spatial resolution. So we can combine this time delay, with a velocity width measurement and use virial product to get an estimate of the black hole mass. This method does not depend on the angular resolution and can be used for high or low luminosity at objects at great distances. And it's also very important for cosmology too. So in principle, we can do this technique on any quasar, but in practice, over the past few years, it's been only done for 60 Aegeans for a shift of less than 0.3. And as we talk today, we'll understand why this is the case so far. One of the main byproducts of reverberation mapping is the simple scaling relation between the radius of the broadline region in H beta and the continuum luminosity. This is often used as a secondary method of mass measurement. You can use this for a large sample of quasars, very distant quasars, and then you can use simple modest spectral resolution to get an estimate of the luminosity, and from that get an estimate of the black hole mass. However, one needs to note that this has been only done for H beta, and this is only calibrated for local low redshift targets. And in fact, if we look at if we add in more targets in this scaling relation, you can see the colored points and the figure on the left. If we add more data points, there seems to be an offset to the scaling relation. These are targets that are probing a wider range in parameter space. And this means that the black hole masses that we've been measuring so far from the scaling relation can be wrong. And in terms of the eigenvector 1 plane, which tells us about the diversity of the quasars, the previous RM measurements are probing a narrow range in parameter space. So it seems that to do a better job of estimating black hole mass beyond what we already know, we need to target more diverse sample of quasars, and also target a larger number of quasars, and also target different emission lines. So how do we do this? Here comes the Sloan Digital Sky Survey Reverberation Mapping campaign, the SDSS-RM campaign, which has started from 2014 and is planning to continue all the way to 2026 as a part of Black Hole Mapper SDSS-5 observations. The campaign targets, as part of the SDSS-RM portion of it at least, has targeted 850 quasars in spectroscopy and photometry. We have photometry from two different sites, and the only thing here is the only cut on our sample selection is through the cut on the magnitude limit. So in any way, it's trying to produce a less biased survey by expanding the RM sample in its physical properties in terms of luminosity, redshift, and mass. Now, in terms of what the before SDSS-RM, what the parameter space looked like, this is what we had, where we have the black hole masses on the y-axis and redshift on the x-axis. You can see a number of H-beta targets in low redshift, very few targets from MG2 and in mid redshift range, and then also at high redshift we have carbon-4 measurements. After SDSS-RM has been able to do their measurements, we've been able to add about 50 targets in H-beta and another 50 in MG2, and then also another 50 in carbon-4. So overall, we've been able to expand and sort of fill this parameter space between low and high redshift range and adding 150 more RM-based black hole masses from 3 different emission lines. Now, our campaign is an industrial scale survey, so we need to have a good handle on the statistical properties of these measurements. We often deal with seasonal gaps and aliasing in our measurements, so we need to have apply statistical priors on our detectability. But in general, what we are looking for is single well-detected peaks in our lag measurements and lags that are significant from 0 and a false positive rate of about 10%. Now, this ensures that if all of our measurements were purely due to noise, we would have, and not due to physical processes, we would have a symmetric profile at the bottom panel, which shows the lag measurements. But even before applying these statistical criteria, we see that there's a positive excess on the positive lag measurements, which means that we are actually measuring physical reverberation rather than just pure noise. So, so in summary, what I've told you so far is that we can use physical sizes. We can use light echoes to measure physical sizes through reverberation mapping. And to do that, we need multi-epoch monitoring that usually takes about months to years. And SDSS-RM has already tripled the previous sample of black hole mass measurements with RM studies. And this has been a huge expansion to, in terms of the parameter space in redshift, accretion rate, and luminosity. Now, I'd like to shift gears a little bit, still within the realm of reverberation mapping, but talk about something slightly different. So it turns out we can use reverberation mapping to study the accretion disk itself. This is often known as disk reverberation mapping or continuum reverberation mapping, where we can use time delay measurements between the hotter inner edges of the accretion disk to outer and cooler edges of the disk. And this method can be used using multiple bands. We can use this to study disk stratifications. We practically do the same kind of analysis, but the difference is that the main difference is that it relies only on photometry. So doing this on our first year of SDSS-RM observations from 850 quasars, we were able to measure 95 quasars that have reliable disk measurements. You can see the parameter space that it's been probing, and you can compare that to the previous work. So it's dramatically expanding the parameter space in terms of redshift and mass. Now, previous studies of continuum disk reverberation, continuum reverberation mapping have been relying on, most of these have been targeted on local targets. These typically measure disks that are about a factor of 3 or 4 times larger than what is expected. And the expectation here is from the Shekharsanyaev 1973 disk model. So local observations have been mostly finding disks that are a factor of 3 times larger. But in terms of their wavelength scaling, and that means how the wavelength is in terms of the wavelength of observation, how does that change? That's been pretty consistent with a factor of 4/3, with a power of 4/3 that the disk scales. In terms of what we find from the SDSS-RM is that we find on average our disks are broadly consistent with Shekharsanyaev model, but at a given mass, we seem to have a large diversity in the disk size. Previous observation again are probing in that range, but what we find is that there seems to be a much broader diversity in the sizes that we measure. And this could be related to anything like black hole spin or efficiency of the quasar, which we need to identify. One of the things that we did in this work is to perform a nonlinear regression to model the disk. That is, to map the temperature size scaling of the accretion disk, and also connect to the mass and luminosity of the target. And through this, we've been able to find consistency between black hole mass and accretion rate, or luminosity as a proxy for accretion rate. But we find that we see an excess dispersion of about 3 days, which could be any missing parameter, whether it's black hole spin or radiative efficiency, which we need to understand what's happening there. As another study here, we targeted a subsample of these targets that have reliable black hole mass measurements from RM. And we targeted them with HST observations over 2 cycles, 72 orbits of HST time. And we were able to the goal of this observation was to see if the UV optical disk is any different than the optical disk that we measure. So we had coordinated observations from HST along with the Liverpool and Las Cumbres network. And for these measurements that are, again, probing a wider range in parameter space, we were able to measure both the UV disk and also the accretion disk stratification. And what we do find is that, again, we find the UV optical disk sizes are broadly consistent with the Shakir-Saniev model, but we now also find that there's this evidence for diffuse nebular emission from Balmer and Arien-2 lines over discrete wavelength bands. So we see an excess in certain bands in our measurements. But broadly, we see that there's a consistency even in the UV optical bands. So it seems that there's a lot more that we do need to understand about the accretion disk itself. How this is gonna move forward is that the SDSS-RM is gonna continue as a part of the SDSS-5 black hole mapper program. This will be a factor of 4 to 5 times larger than the SDSS-RM. It has 5 high cadence reverberation mapping fields and is expected to produce 800 reverberation mapping lags from 1,500 quasars. While SDSS-5 would be amazing in measuring the black hole mass up to redshift of about 3, the cosmological time dilation effect would add a factor of 1 + z to all these variability measurements, meaning that in order to measure these variations, if we typically needed a 3 to 6 months monitoring, we need to expand that to 12 to 24 months of continuous monitoring to be able to use the same kind of method to get a black hole mass estimate. A typical remedy to this is usually to use the black hole mass estimator from the empirical scaling relation between the radius of the broad line region and Aegean continued luminosity. This is the radius luminosity relation that we earlier talked about. The current black hole masses at redshift of about 5 are extremely massive. So it seems that relying on this scaling relation are going to produce masses that are wrong by a factor, overestimated by a factor of 10 or more. And that is unlikely because we don't expect first black holes to be forming so massive in just 1 billion years after the Big Bang. And also we need to know that this is only calibrated for H beta in the low redshift of less than 0.3 universe. So how do we go about this? So SDSS-5 RM observations are going to expand this parameter space in terms of redshift to go about redshift of about 3. And on the other hand, we have SDSS-RM disk measurements that are up to redshift of 1. So we can use the kind of overlap between the SDSS-RM disks and the SDSS-5 black hole mass measurements to create a black hole mass estimator that goes beyond redshift of 3. So when we have, they typically have RM disks, the advantage is that RM disks are weakly dependent on redshift and they rely only on photometry. So that would be a great advantage when we have LSST observations coming up. LSST would be able to use this overlap between the two masses from disks and also from SDSS5 actual RM measurements, and would be able to again calibrate again to go all the way to reach about 5 or 6. This would be amazing when we have the deep drilling fields observations coming up. This will, which will give us the nice monitoring, fast monitoring that we need. We have at least 4 deep drilling fields, and it's going to cover multiple bands, which is going to be amazing for the accretion disk reverberation mapping. So from one aspect, we have the black hole mass sensors that are being built from the SDSS-RM and SDSS-5 black hole mapper observations. And from the other hand, we have this census of accretion disks that then we can combine it to create the mass census of higher redshift. One way to move forward.
3 minutes.
Perfect. One way to move forward with this is to understand what is the connection between the accretion disk and the SCDs of these targets. So we have about 80 SDSS-RM quasars that have reliable masses, but also have contemporaneous observations from XMM, Galaxy, Penn stars, and WISE surveys. So this creates the opportunity for us that if we are able to study UV disk emission as a function of accretion rate, we can reveal if the disks are larger, that means they're cooler and emitting optical, or are smaller and are emitting hot UV. And also the ISCO, the innermost stable circular orbit around the spinning black holes, results in hotter UV emission compared to a non-spinning supermassive black hole, which would be revealed in their SCD shapes. So I want to close up with this census of black hole mass and accretion disk over cosmic time, where from one aspect we have the actual spectroscopy plus photometry from SDSS5 black hole mapper measurements, and we also can expand this when we have LSST observations from both what we already learned from the SDSS-RM up to redshift of 1, and then what we can expand all the way to redshift of 5 and 6. This will be transformational for accretion disk reverberation mapping, but for the parameter space where time dilation effects is going to make it very difficult to do standard reverberation mapping. And with this, I'm going to leave my summary here and happy to take any questions.
Great, thank you. I see one question already on the chat from Seb Hanek. Seb, do you want to just unmute and ask?
Okay, no problem. Yeah, thanks for the talk, really great. So my question was, maybe I misunderstood. You said you want to essentially tie in the spectroscopic reverberation mapping with disk reverberation mapping at higher redshift, but your disk reverberation mapping results seem to imply that there's quite an offset from the standard Croatian Univ disk. So I guess you will introduce quite a big error if you use standard disk relations. So what's your plan, or what's the scatter that we can expect on these high redshift black hole masses?
Yeah, so great question. That is what one of these attempts are. So in order to understand what's causing this is to do a better job of understanding what's going to cause this difference in their SCDs. That's one way to go about it. The other way is that, and I know there are 2 groups in the SDSS-RM that are already working on this. The other aspect is that we need to understand the black hole spin, whether that's a contributing factor, which might be. And so there are ways to tackle this, and there are works that are being done at the moment, but I don't have a good answer to what is exactly we should point our fingers to. But there's definitely an offset. There's many things that we don't understand, and we'll have to figure out what's going on in the next few years that we have.
Other questions? Rosanna.
it's not really a question, it's more a comment. Indeed, we need many measurements because there are several factors which are quite uncertain in this modeling. This is color correction, for example, and it's probably radius dependent. This is the height of this irradiating lamppost which we use, and it actually can be extended. And then, of course, we have this broadline region contribution. So we have those two things which are quite masked, and all that probably is coupled to some extent to Eddington ratio, but we cannot guess from theoretical point of view what is this coupling. So we really need quite a lot of measurement in different sources. Right, so it's more like comment and not really question. I guess you will agree with me.
Yes, absolutely.
Quick question from Matthew O'Dowd, and then we should take a break.
Yeah, so it was interesting to hear you say that that the reverberation measurements of accretion disk size tended to give a factor of 3 larger for the whatever the SS disk expected. Almost exactly the same overestimation of disk size is seen in microlensing measurements of accretion disks in strongly lensed quasars, and I think one of the likely explanations was that it was shown that an inhomogeneous disk would produce that overestimate. I'm wondering if you've thought about similar systematics in the case of reverberation mapping?
That's a good question. I know of a few microlensing observations that have the same prediction as the local predictions for the disk size, but I have not thought about the inhomogeneity. And one of the main limitations here is that when you're dealing with this kind of industrial scale disk measurement, you also want to think about what are the actual observables. And in this case, we are looking at a disk size normalization, which is the first parameter here in purple. Then we have the black hole mass, and then you technically have the efficiency, but what is the observable there? So that's why we relied on luminosity instead of that. So it would be very difficult to have that as observable. And if you have any idea for what to think of, I mean, I know the Shakur-Sanyaev model, we're using this as a sort of basic understanding of the disk size, but there are many things that need to be folded into that to understand what's going on. So I guess all of that would.
So we need let's move any further discussion to the chat or to Slack. I really want to make sure that we get our 10-minute break because we only have 10 minutes. Thanks, Yaseman and the speakers for this afternoon so far. We have one more talk related to reverberation mapping when we come back from the break, and so maybe some of the questions that are relevant here can be asked there, and then we're going to have our discussion. So we'll meet back here in 9 minutes at 1:30 Eastern. Thanks, everyone.
Secunda, my name is Amy Secunda. I'm a grad student at Princeton University. Thank you so much for having me. I'm going to talk about using LSST to probe accretion disk structure by looking at interwaveband lags in quasar photometry. So we just had a talk on disk reverberation mapping. And I just want to review a few key points about that. We're going to, in this talk, refer to that as the short lag. And so these disk reverberation lags, short lags, happen because light from the quasar is reprocessed from the hotter inner disk as it moves outwards to the cooler disk on the light crossing timescale. And so first you receive a short wavelength light, and then you later receive longer wavelength light. And these lags, we call them short because it's just usually on order of a few days, because again, they move at the light crossing timescale, which is obviously fast. What I'm going to talk about is what we've been calling long lags. And so these lags are due to perturbations in the outer disk that then are accreted inwards to the hotter regions of the disk on the inflow or viscous timescale. So they have the opposite sign. They're negative lags because they go from long wavelength light, which leads the short wavelength light, which lags in this case, because again, it's accreted inward through the disk from the colder outer disk to the hotter inner disk. And because it's these lags happen on the inflow time scale, it tends to be more on order of 100 days, so much longer time scale than the short lags, which happen at the light crossing time scale. What's interesting too is because these happen at the inflow time scale, that time scale, the viscous time scale, also depends on things like the scale height. So you have additional information that comes in through the time scale, which you don't have when you're just dealing with the speed of light. So I want to show you some very recent results that me and several collaborators, including Philip Yao, who was first author on this paper and is a fellow grad student at Princeton. So we recently submitted this paper where Philip used high cadence long baseline observations of Ferrel 9 and tried to find a long lag between the different wave bands of observations. And he was actually able to do it. So here's a plot that shows that he found a long lag of -70 days between the W2 band and the Y band, so between around 2,000 and 9,000 angstroms. And this plot was made by using Javelin on the different light curves, which is a cross correlation method. And so again, he detects a long lag of about -70 days. But I want to build kind of a theoretical framework to understand what our expectations are for these long lags. So as I've been saying, they occur on the viscous or inflow time scale. And this time scale has a dependence on radius through omega, which is the orbital frequency. And obviously this R squared here. But we also predict that it'll have a radial dependence because we are saying that H, the scale height of the disk, will have a radial dependence. So we set the scale height proportional to R to some power beta. And when we do this, and then we integrate all these radial dependencies, we get that the inflow time scale is proportional to some constant, and then a factor where we have lambda over lambda naught to the 4/3 times 7/2 minus 2 beta, where if we're just talking about typical disk reverberation mapping and we're assuming kind of the standard thin disk lambda radial dependence, this second part of the exponent goes away and we get lambda over lambda naught to the 4/3. But here we have this additional 7/2 minus 2 beta, again, because we have this additional R dependence in the viscous time scale. And again, in the scale height is where that minus 2 beta comes from. So when we use this theoretical framework and we fit this curve that Philip found using Javelin on Ferrel 9 data, we get that this 4/3 times 7/2 minus 2 beta is equal to minus 5.17, which if we then solve for beta, we find that beta is equal to 3.69, which means that the scale height increases with radius, so you're going to get a flaring of the disk. But even more dramatically than that, if we want to look at the aspect ratio H over R, then we just subtract 1 from beta, and we get that H over R is proportional to R to the 2.69. So that means that the aspect ratio increases as you move outwards in the disk. So this is a pretty dramatic result. It's why you get this really, this flattening as you move outwards in wavelength or out into the outer disk, because as H over R increases, the viscous time scale decreases. So you just, the lag really decreases in these longer wavelengths. So I want to talk about tau naught really quickly. So tau naught has a dependence on the Eddington ratio and the mass of the supermassive black hole. So for traditional short lags, you have Eddington ratio and mass dependence, but to a different power because, again, you have all these additional R dependencies in the time scale. You also have a dependence on the Shakura-Sunyaev viscosity parameter, which here we're just going to hold fixed at 0.1, but you could perhaps learn something about that parameter through looking at long lags. And then last, you have this aspect ratio, H/R, where this is a reference aspect ratio at a reference radiance, which here we take to be the radius corresponding to the W2 band, because that was what we used for the Farrell 9 observations as the reference radius. And we set it at 0.2 here because that is what this H/R at the W2 band would have to be if we wanted to fit the curve that Philip found. And so that gives a scaling of 9 days here. Now you'll notice that this 9 days is a good deal shorter than the minus 70 days that we found for Farrell 9, and that's because I'm using a tau naught that's from the U band to the Y band. So I've kind of marked the U band here as a dashed line, and obviously I'm using U band to Y band because those are the bands available for LSST. And again, if you remember, you get this real flattening of the lag as you move to longer wavelengths, and so you're just going to see a shorter long lag between these two wave bands. Now, a way we can solve this is by looking at higher redshift quasars, which means you'll redshift the inner Huttle regions of the disk where the scale height is smaller into the bands we can observe with LSST. So it might be more useful to look at higher redshift quasars if we want to look for dramatically longer lags. That, for example, would be easier to separate out from the short lag. So anyway, now that we kind of understand some of the parameterizations that go into what this long lag measurement will be, I can show you these plots that show various lag timescales as a function of supermassive black hole mass and Eddington ratio. So the plot on the left-hand side, and again, all of these are from the U to the Y band. On the left-hand side, I have the light crossing timescale or the short lag timescale. And in each plot, the white dot represents the parameters for Farrell 9. And so for Farrell 9 like Aegean, you'll get a short lag of 1 to 10 days, which is typical about what's expected. But then for the long lag, it really strongly depends on what your aspect ratio is, what your H/R is at this reference radius. And that makes sense because it goes as that squared. And so if you have kind of an aspect ratio of 0.03, which is like on the lower end of what is kind of typically assumed, or rather what is typically assumed, then in that case, you would have for Farrell 9, like Aegean, an inflow timescale or a long lag of about 100 to 1,000 days. And so this is where we get our prediction that it'll be about a 100-day lag. But for a much larger aspect ratio of 0.3, which is actually more similar to what we do find for Farrell 9, you get a long lag of only about 1 to 10 days. And so it'll be interesting if we have more than one piece of data, if we're looking at more than just our recent Farrell 9 observations, if we can kind of put any sorts of constraint on this H/R, on this aspect ratio. So now I'll just kind of introduce some of the LSST mocks that I've been doing. So the top panel here shows 2 mock light curves. So first in blue, we have the U band, which I just generated a mock light curve using a damped random walk. And then the Y band is shown in orange, and it's the same damped random walk light curve, except it's been reprocessed with a Gaussian response function that has a minus 40-day lag. So you can clearly see that the Y band leads the U band. Again, the longer wavelength bands will lead the shorter wavelength bands because this lag moves from the outside to the inside of the disk. And so the Y band leads the U band here. So then what I do is I use a few different opsin cadences, and I select out the times at which this region is sampled. So for example, I use the baseline wide fast deep cadence, and then I just take out the points at which this light curve would be observed. And obviously baseline wide fast deep is going to be the most sparse. Then I look at a baseline deep drilling field. So I specifically look at prop ID 4. And so you can see that there are periods of really high cadence, but then there are also these cadences, these periods of no observing, roughly 180 days of high cadence, 180 days of no observations. And these being really, really periodic, I'll show you later, do contaminate our results when we're trying to look for these long lags. So instead, we actually really prefer the rolling cadence for our science. It's a little less strictly periodic than the baseline cadence, and it helps us not get contaminated results. So I take these mock light curves and I run them through Javelin, again, which is a cross correlation method to try and find a long lag. And so here is 3 different examples of Javelin probability distributions for the lag for 3 different cadences. So we have the baseline wide, fast, deep cadence, which you can see has a peak around -40 days, which is the input lag that I put into these mocks. But you also have this pretty big distribution around 150 days. So then we have the baseline deep drilling field. And as I said before, you get this peak around -40 days, but then you also get these really prominent peaks around plus and minus 180 days. And we think that's because of the really clear turn on, turn off cadence that you can see in the light curves. You do get lucky, I guess you would say, in that it's somewhat symmetric. So the median of this probability distribution is around -40. But it's kind of cheating. So then the last is we have I use a rolling deep drilling field, prop ID2, and you can see that this works really well. So there's a really steep 80% of the probability distribution is peaked around -40. You have a little bit of noise, but it's pretty good. So then what I do is I do this 100 times. So I generate 100 different damped random walk light curves and reprocess them. And then I run Javelin on them. And then these show the distributions of those 100 light curves and the medians of their Javelin distribution. So the medians of the Javelin distributions when I run Javelin on 100 different light curves with each of these different cadences. And so for the baseline wide, fast, deep, you get about 50% around the input lag of -40, but you do get some noise. For the baseline deep drilling field, you do get a peak around -40, but again, I kind of it's not that simple because the median is what I'm plotting there, and the median falls in between these 2 big cadence-based peaks. So again, I think the best is the rolling cadence, where you have 99 of the 100 mocks we did fell within -44 and -35. There's one that's kind of out there, but I zoomed in so we could see it better. And you really peak at just longer than -40 days at -41 days. So
can I,
yeah,
it's a good point to interrupt and ask a question. So you say you prefer the rolling cadence, but it looks to me like you just prefer long seasons as opposed to a rolling cadence, if you go back to the light curves you're looking at.
Yeah. I mean, I think that could be true, right? I mean, yeah, I think we prefer a long season is an accurate point. But then there are also, it's not, so actually a nice thing about using the U-band is it's a little less consistent of, say, when the last observation is before the seasonal break, right? So you have this long trailing here. Whereas in the deep drilling field, they're a little more consistent about when the last observation before the seasonal break is, and then we've also done some work looking at the G-band instead of the U-band, just because the G-band has a higher cadence. And I think in a lot of these deep drilling fields, they have the exact last and first observation date on either side of the seasons, and that really contaminates the data. So it's a little bit of a mixture, but I do think long seasons is part of it.
Great, thanks.
I'm sorry,
We have about 3 minutes.
Yeah, so okay, so I'll just show one last result, which is so we've been using Javelin, which is a cross correlation method to try and detect these lags, but we also use a maximum likelihood method Fourier analysis by Zogby et al. And so what's nice about a Fourier analysis is that you can look at the lag as a function of frequency. And this is important if you have, say, a long lag and a short lag, right? Which, you know, the short lags are going to be more consistently present. A long lag could also be present, but you want to be able to disentangle them and not have bias either lag by the presence of the other one. So that's what these Fourier methods are useful for. And so what this Zogby et al. Method, maximum likelihood method, allows you to do is to bin the data in frequency space, because we don't have evenly sampled cadence light curves, and then it fit the maximum likelihood for different values within each bin, different parameters within each bin. So kind of what we have here is at the lowest frequencies, you have this one detection that these are error bars that go off the plot. So I think it's safe to say that that's consistent with 0. And then we have these 4 measurements here that are really close to the input lag of -40 days, especially these lower error measurements here. And then you have this point here that goes positive, and what that's from is something called phase wrapping. And so phase wrapping has the signal kind of oscillate between positive and negative. And that happens at a point shown as the gray line here, 1/2 times the lag signal. So here it would be 1/2 times 40, 1/80. And so you kind of can't really take any of the data to the short frequency, long frequency side of that. Although if you were to have an additional signal from a short lag here, that could be stronger than the phase lag. But so for our purposes, where we just have a long lag, it's actually the results are pretty good, because they're pretty consistent with -40 days below the phase wrapping point. And then what's interesting is that I find that the phase wrapping point tends to be really consistently at 1/2 times the lag that I input. And so this actually might be a really good way to detect these lags, is by looking for where the phase wrapping starts. And so here it's really clear. Overall, when I run this on like 100 different light curves, about half the time you get results that are this clear. So you'll definitely lose some using this method, but getting 50% is pretty good. So anyway, I'll just leave up my summary slide and I'll take any questions.
Great, thanks, Amy. Thanks for getting started when I was having trouble. Lots of comments in the chat, some of which are questions. I think what I'll let people do is just unmute or raise your hand and ask them, because I'm not sure which is a comment and which is a question. Maurizio.
I was just wondering if there are problems with the U-band because it's a sparser cadence and different depth from the other data, or on long time scale, it doesn't really matter.
Yeah, so I think on the long time scale, it doesn't matter. Again, I think we've had more trouble with kind of consistent cadence periodicity. And so the fact that it does have fewer pointings actually messes that up, because it's less periodic. And so we haven't had trouble using the U-band. Again, the results are pretty much the same as if we try and use the G-band. So it hasn't been a problem. I assume if you were looking for a shorter lag, that would be different. The G-band would probably be better to use.
Franz?
So how is this consistent with the lag metric that has been produced? Do you know? So are your results effectively consistent with what they find?
In what?
So there's a lag metric for the OpSims. And so they, what I would initially was going to say was, it would be great if you could put these in a form where they would be relevant to the ongoing discussion of what the cadence wars, as it were. And within that scope, I'm wondering whether the information you have or the suggestions you have are effectively encapsulated already in the lag metric that Angelica and I'm blanking on her name. Anyway, the Serbian group have produced. If that's true, that's great, and we can use those, kind of to kind of promote this. We can discuss this later in the discussion for 45 minutes. It was just, I was thinking about it now. So.
Yeah, no, I'm actually not sure. That would be worth looking into more for me. I mean, I think most people, when they think of lag, are thinking of either broadline region lag or short lag. And so we have been doing some tests of our own short lag, but I know other people are thinking of that. But yeah, I'm not sure if their lag metric is looking for lags as long as 100 days, or measuring LSST's ability to look for them, rather.
Yeah.
Yeah, I was going to just to follow up on what Franz said. It could be very helpful for the purpose of setting what is important for the Rubin cadence. If you could try things out, like how much does season length specifically affect the results? How much does sampling pattern affect the results? And so, and figure out what it is you really want. The good news is that a large number of us in the Aegean Science Collaboration, and I believe also the folks in the Dark Energy Science Collaboration, have been pushing pretty hard for the longest season lengths possible. That's well appreciated. You can look back to our white paper from 2018. And so I think it's widely recognized that long seasons are very good for a wide variety of science cases, for AGNs and more broadly. So if you are pushing that further, that's great. On the other hand, if you are saying that you want something else, that it isn't the season length, but it's something else, having it very clear exactly what it is that you want would be helpful.
Yeah,
Thanks.
That sounds great. Yeah.
Okay, great.
Yeah, I would second or third that, right? In the sense that, some of the supernova people want really extreme rolling cadences, right? So you have to be careful, right? If you say we want a rolling cadence, the question is, well, are you willing to only observe once every 3 years at high cadence, kind of thing, right? And if you just really want long seasons, then that's what we should say, right?
Yeah. From experience, you have to be pretty careful and specific about exactly what it is you want. If you just say, I like this baseline proposal and I don't like that one, people may interpret that to say things that you're not trying to say.
Yeah, thank you. That's really, really useful feedback.
So, that might be, thanks, Amy, that may be a good segue to talking about the SCOC stuff, although, I'm happy to spend 10 minutes talking about other things that came up so far today before we switch to that, if anybody wants to bring anything up.
Well, let me just say quickly, Gordon, I'm going to stop the recording now so we can just speak freely. Franz, if you feel like you really want this recorded, I'm happy to record it with a separate file. Do you want this recorded, or should this just be open discussion?
It really depends on if you want to include the